Long before telescopes revealed the true nature of this celestial wonder, human beings across diverse cultures noticed something unusual about a particular patch of sky in the northern hemisphere. There, nestled within a constellation that bore the name of an Ethiopian princess from Greek mythology, existed a softly glowing presence that defied easy explanation. This was not a star, for it lacked the sharp twinkling quality of the thousands of stellar points surrounding it. Neither was it a planet, those wandering lights that ancient observers tracked with such careful attention. Instead, this object possessed a quality entirely its own, a diffuse, cloud-like appearance that seemed to hover at the very edge of human perception. The earliest recorded observation of what we now call the Andromeda Galaxy comes from the Persian astronomer Abd al-Rahman al-Sufi, who lived during the 10th century in the city of Isfahan. In his remarkable work, The Book of Fixed Stars, completed around the year 964, al-Sufi meticulously catalogued the night sky, combining his own careful observations with the classical knowledge passed down from ancient Greek astronomers. When he came to describe the constellation of Andromeda, he noted something that previous cataloguers had overlooked or perhaps dismissed as unimportant. He described a nebulous smear, or little cloud, positioned near the mouth of a larger celestial fish figure that Arab astronomers recognized in that region of the sky. Al-Sufi's observation represents a profound moment in human history, though neither he nor anyone else at the time could have understood its true significance. In noting this small cloud, this Persian scholar became the first person to document the existence of a galaxy beyond our own. He was looking at a collection of 1 trillion stars, a vast cosmic metropolis located over 2 million light-years from Earth, and yet to his eyes and to the understanding of his era, it appeared as nothing more than a curious atmospheric phenomenon, or perhaps some unusual type of star. The gentle glow that al-Sufi recorded had likely been noticed by countless observers before him, stretching back into the depths of prehistory. On clear, moonless nights, far from any source of artificial illumination, the Andromeda Galaxy is visible to the unaided human eye as a faint, elongated patch of light. Our ancient ancestors, who spent far more time beneath dark skies than most modern humans ever will, must have noticed this peculiar smudge among the stars. Yet without written records, we can only imagine what stories they might have told about it, what significance they might have attached to this ghostly presence in the autumn heavens. The Greeks, whose mythology would eventually lend its name to both the constellation and the galaxy, developed an elaborate story to explain the stars in this region of the sky. According to their legends, Andromeda was a princess of Ethiopia, the daughter of King Cepheus and Queen Cassiopeia. Her mother's vanity brought disaster upon their kingdom when Cassiopeia boasted that her daughter's beauty surpassed even that of the Nereids, the sea nymphs who attended the god Poseidon. Enraged by this hubris, Poseidon sent a terrible sea monster named Cetus to ravage the Ethiopian coast. The desperate king consulted an oracle who revealed that only the sacrifice of Andromeda could appease the gods and save his kingdom. And so the princess was chained to a rocky outcrop by the sea, left to await her fate as the monster approached. Yet in the way of Greek myths, a hero appeared at the crucial moment. Perseus, fresh from his victory over the Gorgon Medusa, happened to be flying overhead on his winged sandals. He saw the beautiful princess in her distress, fell instantly in love, and swooped down to rescue her. Using the severed head of Medusa, whose gaze could turn any living creature to stone, Perseus petrified the sea monster and claimed Andromeda as his bride. The gods, pleased by this tale of heroism and love, placed all the principal characters among the stars. There you can find them still on any clear autumn evening in the northern hemisphere. Cassiopeia, with her distinctive W-shaped pattern, Cepheus the king nearby, Perseus the hero with his sword raised, Andromeda the princess with her arms outstretched, and even Cetus the sea monster swimming through the celestial waters below. The faint glow of the Andromeda Galaxy lies within the boundaries of the princess's constellation, though the ancient Greeks did not distinguish it as a separate object worthy of its own mythology. This mythological framework persisted for centuries, shaping how European astronomers thought about and described this region of the sky. When they spoke of the Andromeda Nebula, as the galaxy was long called, they were referring to an object within a constellation named for a princess from a story about vanity, sacrifice, and heroic rescue. The romantic and dramatic associations of the myth lent a certain poetry to astronomical discussions, even as the scientific understanding of the object itself remained frustratingly incomplete. Islamic astronomers of the medieval period made significant contributions to our understanding of the night sky, preserving and extending the knowledge of ancient Greece while adding their own careful observations. The work of al-Sufi was particularly important, as his Book of Fixed Stars became a standard reference that influenced astronomical thinking for centuries. His description of the little cloud in Andromeda was copied and recopied by subsequent scholars, ensuring that this observation was not lost to history. The Arab astronomers developed their own constellation figures and star names, many of which persist in modern astronomy. When you hear names like Alpheratz, the brightest star in the Andromeda constellation, or Mirach and Almach, other prominent stars in the same region, you are hearing echoes of Arabic astronomical tradition. These scholars looked at the same skies that the Greeks had mapped, but they brought their own cultural perspectives and observational techniques to the task of understanding the heavens. As centuries passed and astronomical knowledge spread across cultures and continents, the mysterious nebula in Andromeda attracted increasing attention. European astronomers of the Renaissance and early modern period, equipped with improving instruments and a growing spirit of scientific inquiry, began to examine this object more carefully. Yet even with the telescopes of the 17th and 18th centuries, the true nature of the Andromeda Nebula remained elusive. It appeared as a fuzzy, elongated glow, clearly different from ordinary stars, but impossible to resolve into any recognizable structure. The German astronomer Simon Marius claimed to have observed the Andromeda Nebula through a telescope in 1612, describing it as resembling the light of a candle shining through horn. This poetic description captures something essential about the galaxy's appearance through early telescopes, that soft, diffuse quality that distinguishes it from the sharp points of individual stars. Marius was one of the first to examine this object with optical aid, though his observations did little to clarify what the nebula actually was. Throughout the 17th and 18th centuries, astronomers accumulated a growing catalogue of similar nebulous objects scattered across the sky. The French astronomer Charles Messier, who was primarily interested in hunting comets, compiled a famous list of objects that might be confused with comets, but were actually permanent features of the heavens. The Andromeda Nebula received the designation Messier 31 or M31 in his catalogue, a name that astronomers still use today, alongside the more formal designation of NGC 284. The question of what these nebulae actually were provoked considerable debate among astronomers of this era. Some believed they were clouds of luminous gas within our own stellar system, perhaps regions where new stars were forming, or the remnants of stars that had died. Others speculated that at least some nebulae might be distant collections of stars, so far away that even the best telescopes could not resolve them into individual points of light. This latter idea which would eventually prove correct for the Andromeda Nebula, was remarkably prescient, but it would take more than a century of additional observation and theoretical development before it could be confirmed. The philosopher Immanuel Kant, writing in the mid-18th century, proposed that some nebulae might be island universes, vast collections of stars similar to our own Milky Way, but located at immense distances from us. This concept, elegant in its simplicity, suggested that the universe might be far larger and more complex than anyone had previously imagined. Rather than a single system of stars with our sun somewhere within it, the cosmos might contain countless such systems, each a galaxy in its own right, separated by gulfs of empty space, almost too vast to comprehend. Kant's island universe hypothesis remained controversial for over a century and a half. The technology to test it simply did not exist. Telescopes could reveal that some nebulae had spiral structures, beautiful pinwheel patterns that suggested rotation and organized motion, but they could not determine whether these spirals were relatively nearby gas clouds or incredibly distant star systems. The Andromeda Nebula, with its elongated shape and hints of internal structure, became a central object in this debate. As the 19th century progressed, astronomers made increasingly detailed observations of M31. They noted its elliptical outline, its brighter central region, and the dark lanes that seemed to cross its disk. Some observers reported glimpsing what appeared to be individual stars within the nebula, though others disputed these claims. The spectroscope, a new tool that allowed astronomers to analyze the light from celestial objects, provided additional clues. The spectrum of the Andromeda Nebula resembled that of starlight rather than glowing gas, suggesting that it might indeed be composed of stars too distant and numerous to see individually. Yet even as evidence accumulated in favour of the island universe hypothesis, many astronomers remained sceptical. The distances implied by this theory seemed almost impossibly large. If the Andromeda Nebula were truly a galaxy comparable to our own Milky Way, it would have to be millions of light years away, a distance that strained the imagination and raised troubling questions about the scale of the cosmos. Some researchers proposed alternative explanations that kept the nebula within our own galaxy, perhaps as a peculiar type of star system or a region of unusual stellar activity. The cultural significance of Andromeda extended beyond the scientific community during this period. Artists and writers found inspiration in the mysterious nebula and the mythology associated with its name. The image of the chained princess awaiting rescue became a popular subject for paintings and sculptures, while the astronomical object itself represented the allure of the unknown, a symbol of cosmic mysteries yet to be solved. The Andromeda Nebula occupied a unique position in the public imagination, familiar enough to be recognized by name, yet strange enough to provoke wonder and speculation. As the 20th century dawned, the stage was set for a revolution in our understanding of the universe. New telescopes of unprecedented size were being constructed. Photographic techniques were improving rapidly, and theoretical frameworks were emerging that would eventually explain the observations that had puzzled generations of astronomers. The Andromeda Nebula, that faint smudge first recorded by a Persian scholar 1,000 years earlier, was about to reveal its true nature and transform humanity's conception of the cosmos forever. Section 2. Ancient Observations and the Path to Discovery. The journey from Al-Sufi's little cloud to our modern understanding of the Andromeda Galaxy spans more than a millennium of human curiosity, technological innovation, and intellectual courage. Each generation of observers added something to our knowledge, even when they could not fully comprehend what they were seeing. This gradual accumulation of information, punctuated by occasional leaps of insight, represents one of the great detective stories in the history of science. Following Al-Sufi's initial documentation, the Andromeda Nebula appeared sporadically in astronomical records over the following centuries. Medieval European astronomers, working largely from translations of Arabic texts, were aware of the object, but added little to what Al-Sufi had observed. The prevailing cosmological framework of the time, based on the ancient Greek model of crystalline spheres carrying the planets and stars around a central Earth, had no place for diffuse nebulous objects. They were anomalies, curiosities that did not fit neatly into the accepted picture of the heavens. The invention of the telescope in the early 17th century opened new possibilities for astronomical observation. When Galileo Galilei turned his primitive instrument toward the sky in 1609 and 1610, he discovered wonders that challenged centuries of received wisdom. He saw mountains on the moon, spots on the sun, moons orbiting Jupiter, and countless stars invisible to the naked eye. The Milky Way, that luminous band stretching across the sky, resolved into innumerable individual stars when viewed through his telescope. The universe was clearly far more complex and populous than anyone had suspected. Yet even Galileo's telescope, revolutionary as it was, could not reveal the true nature of the Andromeda Nebula. The object remained a fuzzy glow, its individual stars far too distant to be distinguished with the optical technology of the early 17th century. Simon Marius, a German astronomer who was one of the first to observe Andromeda telescopically, provided a description that emphasized this nebulous quality. His comparison to candlelight seen through horn captures the soft, diffuse appearance that would characterize observations of this object for the next 3 centuries. As telescopes improved throughout the 17th and 18th centuries, astronomers began to catalogue the various nebulous objects visible in the night sky. These nebulae, as they were collectively called, presented a diverse array of appearances. Some were nearly circular, others elongated. Some showed hints of internal structure, while others appeared uniformly smooth. A few could be resolved into clusters of individual stars when viewed through sufficiently powerful instruments, but many, including the Andromeda Nebula, stubbornly resisted such resolution. The French astronomer Charles Messier, working in the latter half of the 18th century, compiled his famous catalogue primarily as a practical aid for comet hunters. Comets, when first spotted, often appear as faint, fuzzy objects that can easily be confused with permanent nebulae. Messier sought to create a list of objects that were definitively not comets, allowing observers to quickly eliminate known nebulae from consideration when searching for new cometary visitors. His catalogue, eventually containing 110 objects, became one of the most enduring references in amateur and professional astronomy alike. Messier assigned the number 31 to the Andromeda Nebula, and this designation remains in common use today. The entry in his catalogue describes the object's position and general appearance, noting its elongated shape and relatively bright central region. Messier made no attempt to explain what the nebula actually was, content to simply document its existence and location. This practical approach was characteristic of much 18th century astronomy, which focused on careful observation and cataloguing rather than theoretical speculation. The question of the nebulae's true nature became increasingly pressing as the catalogue of known objects grew. William Herschel, the German-born astronomer who discovered Uranus and spent decades surveying the heavens from England, made the study of nebulae one of his primary interests. Using telescopes of his own construction, larger and more powerful than any that had come before, Herschel observed thousands of nebulous objects and attempted to classify them into meaningful categories. Herschel's observations led him to propose that at least some nebulae were indeed distant collections of stars, systems so remote that their individual members blurred together into a continuous glow. He called these objects island universes, a term that would later be revived and popularized by others. Yet Herschel was not consistent in this view, and his opinions shifted over the course of his long career. The evidence available to him was simply insufficient to settle the question definitively. The Andromeda Nebula received particular attention from Herschel, who noted its impressive size and brightness compared to other nebulous objects. He observed that it seemed to have a brighter central condensation surrounded by a more diffuse outer region, a structure suggestive of some underlying organization. Yet even Herschel's magnificent telescopes could not resolve M31 into individual stars, leaving its true nature uncertain. The 19th century brought new tools and techniques to astronomical observation. Photography, developed in the 1830s and 1840s, gradually found applications in astronomy, allowing observers to create permanent records of celestial objects and to detect details too faint for the human eye to perceive directly. Spectroscopy, the analysis of light by spreading it into its component wavelengths, provided a powerful new method for determining the physical properties and chemical composition of distant objects. When astronomers turned their spectroscopes toward the Andromeda Nebula, they found that its light resembled the combined output of many stars rather than the emission lines characteristic of glowing gas clouds. This was an important clue, suggesting that M31 might indeed be a stellar system rather than a gaseous nebula. Yet the interpretation of spectroscopic data was still in its early stages, and alternative explanations could not be ruled out entirely. The application of photography to the study of Andromeda yielded dramatic results. Long exposure photographs revealed details invisible to visual observers, including hints of spiral structure in the nebula's outer regions. The British astronomer Isaac Roberts produced a famous photograph of M31 in 1888 that clearly showed the galaxy's spiral arms for the first time. This image, which required an exposure of over 4 hours, transformed scientific and public perceptions of the object. Here was evidence of organized structure on a grand scale, suggesting rotation and dynamic processes within the nebula. Roberts himself believed that his photograph showed a solar system in formation, with the spiral arms representing material that would eventually condense into planets. This interpretation, while incorrect, reflects the difficulty of grasping the true scale of what the photograph revealed. The idea that this spiral structure might span hundreds of thousands of light years and contain billions of stars was simply too far removed from everyday experience to seem plausible. As the 19th century drew to a close, the debate over the nature of spiral nebulae like Andromeda remained unresolved. Observations had accumulated that seemed to support the island universe hypothesis, but definitive proof remained elusive. The key obstacle was distance. If astronomers could determine how far away the Andromeda Nebula was located, they could settle the question once and for all. A nearby object within our own Milky Way system would be one thing. An object millions of light years distant would necessarily be a galaxy in its own right. Measuring astronomical distances is one of the most challenging problems in the field. For relatively nearby stars, astronomers can use the method of parallax, observing how a star's apparent position shifts as Earth moves around its orbit. This geometric technique, analogous to how our two eyes provide depth perception by viewing objects from slightly different angles, works well for stars within a few hundred light years, but becomes impractical for more distant objects, where the parallax shift is too small to measure accurately. For the Andromeda Nebula, parallax measurements were hopeless. If the object were as distant as the island universe hypothesis suggested, its parallax would be far below the detection threshold of any 19th century instrument. Other methods for estimating distance existed, but they all relied on assumptions that might or might not be valid. The size of the nebula, its apparent brightness, the motions of features within it, all of these could provide distance estimates, but only if astronomers knew certain properties of the object that were themselves uncertain. One approach involved studying novae, stars that suddenly flare up to many times their normal brightness, before fading back to obscurity. Several novae had been observed in the Andromeda Nebula, including a particularly bright one in 1885 that briefly rivaled the entire nebula in luminosity. If astronomers could determine the intrinsic brightness of these novae, they could compare it to their apparent brightness as seen from Earth and calculate the distance. Unfortunately, the true nature of novae was poorly understood at the time, and different assumptions about their luminosity led to wildly different distance estimates. The question of the nebulae came to a head in the early 20th century, as new observational capabilities made more definitive answers seem possible. Large telescopes were being constructed, including the 60-inch and 100-inch reflectors at Mount Wilson Observatory in California. These instruments, situated at a high-altitude site with excellent atmospheric conditions, represented the cutting edge of astronomical technology. They would play a crucial role in resolving the great debate about the nature of spiral nebulae. The intellectual climate was also shifting. Einstein's theories of relativity, published in 1905 and 1915, had revolutionized physics and opened new ways of thinking about space, time, and the structure of the universe. Astronomers were increasingly willing to consider radical possibilities, including the idea that the cosmos might be far larger and more complex than traditional models suggested. The stage was set for a transformation in human understanding of our place in the universe. Section 3, The Great Debate and Edwin Hubble's Revolution. The early decades of the 20th century witnessed one of the most consequential scientific controversies in the history of astronomy. At stake was nothing less than our understanding of the scale and structure of the universe. Were the spiral nebulae, including the Great Nebula in Andromeda, relatively nearby objects within our own Milky Way system, or were they distant galaxies comparable to the Milky Way itself, separated from us by almost unimaginable gulfs of empty space? This question, which had simmered for over a century, came to a dramatic focus on April 26, 1920, when two distinguished astronomers faced off in what became known as the Great Debate. The venue was the Smithsonian Museum of Natural History in Washington, D.C., and the occasion was a meeting of the National Academy of Sciences. Harlow Shapley of Mount Wilson Observatory argued that the spiral nebulae were relatively small, nearby objects, while Heber Curtis of Lick Observatory maintained that they were distant island universes. Shapley had made his reputation by studying the distribution of globular clusters, dense spherical collections of ancient stars that orbit the centre of the Milky Way. His work had revealed that our galaxy was far larger than previously thought, and that the Sun occupied a position far from the galactic centre. This expanded view of the Milky Way made it seem plausible that spiral nebulae might be contained within it, perhaps as peculiar subsystems or regions of unusual stellar activity. Curtis, by contrast, had carefully studied the spiral nebulae themselves and found evidence that they were external to our galaxy. He noted that novae in the Andromeda Nebula were on average much fainter than novae in the Milky Way, suggesting that they were located at far greater distances. He also pointed to the dark lanes visible in some spiral nebulae, which resembled the obscuring dust clouds known to exist in our own galaxy. If spirals were external systems seen from outside, such dust lanes would be expected. The debate itself while intellectually stimulating, did not resolve the controversy. Both astronomers presented compelling arguments, but neither could offer definitive proof. The observational evidence was simply too ambiguous to settle the question. What was needed was a reliable method for measuring the distances to spiral nebulae, one that did not depend on uncertain assumptions about their intrinsic properties. The breakthrough came from an unexpected source, a particular type of variable star known as a Cepheid. These stars pulsate regularly, brightening and dimming over periods ranging from a few days to several weeks. In 1912, Henrietta Swan Leavitt, an astronomer working at Harvard College Observatory, discovered a remarkable relationship among Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere. Leavitt found that brighter Cepheids had longer pulsation periods. This period-luminosity relationship meant that by measuring how long a Cepheid took to complete one cycle of brightening and dimming, astronomers could determine its intrinsic luminosity. Comparing this intrinsic brightness to the star's apparent brightness, as seen from Earth, would then reveal its distance. Cepheids became standard candles, objects of known luminosity that could be used to measure cosmic distances. The application of Leavitt's discovery to the spiral nebula question required telescopes powerful enough to detect individual Cepheid stars in these distant objects. This is where the great reflectors at Mount Wilson Observatory entered the story. The 60-inch telescope, completed in 1908, was the largest in the world at the time, and it was soon joined by the even more powerful 100-inch Hooker telescope, which saw first light in 1917. Edwin Hubble, a young astronomer who joined the Mount Wilson staff in 1919, took up the challenge of searching for Cepheids in the Andromeda Nebula. Night after night, he photographed M31 with the great telescopes, patiently accumulating images that might reveal variable stars among the nebula's countless points of light. The work was painstaking, requiring careful comparison of photographs taken on different nights to identify stars that had changed in brightness. On October 6, 1923, Hubble made a discovery that would change astronomy forever. Examining a photographic plate of the Andromeda Nebula, he identified what he initially thought was a nova, a star that had suddenly flared in brightness. But as he gathered more observations over the following weeks, he realized that this star was not a nova at all. It was varying in a regular, periodic manner, brightening and dimming with a cycle of about 31 days. It was a Cepheid variable. Hubble marked his photographic plate with the notation VAR to indicate the variable star, and this historic plate is now preserved at the Carnegie Observatories. Using Leavitt's period-luminosity relationship, he calculated the distance to this Cepheid and, by extension, to the Andromeda Nebula itself. The result was staggering, approximately 900,000 light-years, far beyond the boundaries of the Milky Way, as Shapley had defined them. Modern measurements have revised this figure upward to about 2.5 million light-years, as astronomers have refined their understanding of the Cepheid distance scale. But even Hubble's initial estimate was sufficient to prove the essential point. The Andromeda Nebula was not a nebula at all, in the sense of a cloud of gas within our galaxy. It was an entirely separate galaxy, a vast stellar system comparable to or even larger than the Milky Way, located at an almost incomprehensible distance from Earth. Hubble announced his findings at a meeting of the American Astronomical Society on January 1, 1925, and the astronomical community quickly accepted his conclusions. The great debate was over. The island universe hypothesis, first proposed by Kant in the 18th century and championed by Curtis in 1920, had been vindicated. The universe was suddenly revealed to be far larger and more populous than anyone had imagined. The implications of Hubble's discovery extended far beyond the specific case of the Andromeda Galaxy. If M31 was an external galaxy, then so were the countless other spiral nebulae scattered across the sky. Each of these objects was a stellar system in its own right, containing billions of stars, and the universe contained not just one such system, but uncountable multitudes. The scale of the cosmos had expanded by a factor of millions in a single stroke. Hubble continued his observations of galaxies throughout the 1920s and 1930s, making additional discoveries that further transformed our understanding of the universe. He developed a classification system for galaxies based on their shapes, distinguishing between elliptical galaxies, spiral galaxies like Andromeda and the Milky Way, and irregular galaxies with no clear structure. This classification scheme, often depicted as a tuning fork diagram, remains in use today. Even more dramatically, Hubble discovered that distant galaxies are moving away from us, and that the speed of their recession is proportional to their distance. This relationship, now known as Hubble's law, provided the first observational evidence that the universe is expanding. The implications were profound. If galaxies are moving apart today, they must have been closer together in the past. Tracing this expansion backward in time led eventually to the concept of the Big Bang, the explosive origin of the universe from an initial state of extreme density and temperature. The Andromeda Galaxy played a role in this discovery as well, though in a somewhat paradoxical way. When Hubble and his colleague Milton Humason measured the motion of M31 using the Doppler shift of its spectral lines, they found that it was not receding from us at all. Instead, the Andromeda Galaxy is approaching the Milky Way at a speed of about 110 kilometers per second. This blue shift, indicating motion toward us rather than away, seemed to contradict the pattern of universal expansion. The resolution of this apparent paradox lies in the distinction between the overall expansion of the universe and the local motions of individual galaxies. The Milky Way and Andromeda are gravitationally bound to each other as members of the local group, a small cluster of galaxies that move together through space. Within this group, gravitational attraction can overcome the general expansion, causing galaxies to approach each other. On larger scales beyond the local group, the expansion dominates, and galaxies are indeed receding from us. The approach of Andromeda toward the Milky Way has profound implications for the distant future of both galaxies, a topic we will explore in detail later. For now, it is enough to note that Hubble's measurements revealed M31 to be not just a distant neighbour, but an approaching one, destined to interact with our galaxy in the far future. Hubble's work on the Andromeda Galaxy and other external systems earned him recognition as one of the greatest astronomers of the 20th century. The Hubble Space Telescope, launched in 1990 and still operating today, bears his name in tribute to his contributions. This orbiting observatory has itself made countless observations of the Andromeda Galaxy, revealing details impossible to see from Earth's surface, and continuing the tradition of discovery that Hubble began with his ground-based photographs nearly a century ago. The transformation in our understanding of the universe that occurred in the 1920s can hardly be overstated. Before Hubble's discovery, it was reasonable to believe that the Milky Way constituted the entire universe, a single island of stars floating in an infinite void. After his work, we knew that our galaxy was just one among billions, a typical spiral system in a cosmos of unimaginable vastness. The Andromeda Galaxy, that faint smudge first noted by Al-Sufi 1,000 years earlier, had served as the key that unlocked this new understanding. Section 4. Andromeda's Cosmic Address and Neighbourhood. The Andromeda Galaxy does not drift alone through the void of intergalactic space. Like our own Milky Way, it exists within a cosmic neighbourhood, a gravitationally bound collection of galaxies that astronomers call the local group. Understanding Andromeda's place within this larger structure helps us appreciate both its significance and its relationship to our own galactic home. The local group is a modest gathering by cosmic standards, containing somewhere between 80 and 100 known galaxies, depending on how one counts the smallest and faintest members. This number may seem impressive, but compared to the great galaxy clusters that contain thousands of members, our local neighbourhood is decidedly small scale. The local group spans roughly 10 million light-years in diameter, a vast distance by human standards, but a mere speck against the observable universe, which extends for tens of billions of light-years in every direction. Within this local neighbourhood, two galaxies dominate all others, the Milky Way and Andromeda. These twin spirals are by far the largest and most massive members of the local group, containing between them the great majority of the group's total stellar mass. They are like two great cities in a rural landscape, surrounded by smaller towns and villages represented by the dozens of dwarf galaxies that orbit around them. The Andromeda Galaxy lies approximately 2.537 million light-years from Earth, a distance so vast that light itself requires over 2.5 million years to traverse it. When you look at Andromeda in the night sky, you are seeing light that left the galaxy during the early Pleistocene epoch on Earth, a time when our ancestors were just beginning to develop the stone tools that would eventually lead to human civilization. The Andromeda you observe tonight is not the Andromeda of today, but a snapshot from deep in the past, preserved in the photons that have travelled across the cosmic gulf to reach your eyes. This concept of looking back in time is one of the most profound aspects of astronomical observation. Because light travels at a finite speed, approximately 792 kilometers per second, every glimpse of a distant object is necessarily a glimpse into history. The farther away something is, the older the light we receive from it. When astronomers study galaxies billions of light-years distant, they are witnessing the universe as it existed billions of years ago, long before Earth or the Sun had formed. The Andromeda Galaxy, relatively nearby in cosmic terms, offers a view into a past that is ancient by human standards, yet recent by the measure of the universe itself. To truly appreciate Andromeda's position in space, we must first understand the hierarchical structure of the cosmos. The universe is not uniformly filled with galaxies scattered randomly like dust motes in a sunbeam. Instead, gravity has organized matter into a complex web of structures at various scales. Stars gather into galaxies, galaxies cluster into groups and clusters, and these larger assemblages connect through filaments and walls to form the cosmic web, the largest known structure in the universe. At the smallest scale of this hierarchy, individual stars orbit within galaxies. Our Sun is one of roughly 200 to 400 billion stars in the Milky Way, occupying a position in one of the spiral arms about 26,000 light-years from the galactic center. The Milky Way itself is a barred spiral galaxy, meaning it has a central bar-shaped structure from which the spiral arms extend. This is our immediate cosmic home, the stellar city in which our solar system resides. Moving up the hierarchy, we find that the Milky Way is not isolated. It belongs to the local group, that modest collection of galaxies bound together by their mutual gravitational attraction. The local group is dominated by its two largest members, the Milky Way and Andromeda, but it contains many smaller galaxies as well. Some of these are satellites of the two great spirals, orbiting around them much as moons orbit planets. Others occupy more independent positions within the group, moving through the shared gravitational field created by all the members together. The third largest galaxy in the local group is the Triangulum Galaxy, also known as Messier 33, or simply M33. This spiral galaxy lies about 2.73 million light-years from Earth, slightly farther than Andromeda, and contains roughly 40 billion stars. While impressive by most standards, Triangulum is considerably smaller than either the Milky Way or Andromeda. It may be a satellite of Andromeda, gravitationally bound to its larger neighbour, though this remains a subject of ongoing research. Beyond these three spirals, the local group contains dozens of dwarf galaxies, small stellar systems that range from a few billion stars down to just a few million or even less. Many of these dwarf galaxies are so faint and diffuse that they were only discovered in recent decades, as astronomical surveys became sensitive enough to detect their subtle presence against the background of more distant objects. The dwarf galaxies of the local group provide valuable laboratories for studying stellar evolution, dark matter, and the processes by which galaxies form and grow. The Milky Way has its own retinue of satellite galaxies, the most famous being the large and small Magellanic Clouds. These irregular galaxies, visible to the naked eye from the southern hemisphere, are relatively close to us at distances of about 160,000 and 200,000 light-years, respectively. They are slowly being pulled apart by the Milky Way's gravity and will eventually merge with our galaxy entirely. Other Milky Way satellites include the Sagittarius Dwarf Elliptical Galaxy, which is currently in the process of being absorbed by our galaxy, and numerous ultra-faint dwarf galaxies discovered in recent sky surveys. Andromeda, being larger and more massive than the Milky Way, possesses an even more extensive system of satellite galaxies. At least 20 confirmed satellites orbit M31, and the true number may be considerably higher as astronomers continue to discover faint dwarf galaxies in its vicinity. The most prominent of these satellites are M32 and M110, both of which are visible in amateur telescopes as small fuzzy patches near the main body of Andromeda. M32, also known as NGC 221, is a compact elliptical galaxy that lies very close to Andromeda's disk, appearing to sit almost on top of the larger galaxy when viewed from Earth. This small but dense stellar system contains several billion stars packed into a region only about 6,500 light-years in diameter. M32 is unusual among dwarf galaxies for its high stellar density and the presence of a supermassive black hole at its centre, estimated to contain between 1.5 and 5 million solar masses. Some astronomers believe that M32 was once a much larger galaxy that has been stripped of most of its outer stars through gravitational interactions with Andromeda. M110, or NGC 205, is a dwarf elliptical galaxy located on the opposite side of Andromeda from M32. It is larger but less dense than M32, spanning about 17,000 light-years and containing an estimated 10 billion stars. Unlike most elliptical galaxies, M110 shows evidence of recent star formation, with young blue stars visible in its central regions. This suggests that it may have retained some gas and dust despite its interactions with Andromeda, or that it has recently acquired new material through some process not yet fully understood. The other satellite galaxies of Andromeda are generally smaller and fainter than M32 and M110, requiring larger telescopes to observe. They include dwarf spheroidal galaxies, dwarf elliptical galaxies, and a few irregular dwarfs. Many of these satellites show signs of tidal disturbance, their shapes stretched and distorted by Andromeda's powerful gravitational influence. Some are likely in the process of being absorbed by their giant host, their stars gradually being stripped away and incorporated into Andromeda's outer halo. The distribution of satellite galaxies around Andromeda has provided important insights into the nature of dark matter and the processes of galaxy formation. Observations have revealed that many of Andromeda's satellites lie within a thin plane, a structure that was not predicted by standard models of galaxy formation. This so-called plane of satellites has sparked considerable debate among astronomers, with some arguing that it challenges our understanding of dark matter, while others propose explanations within the standard framework. Beyond the local group, the cosmic neighbourhood extends to larger structures. The local group is part of the Virgo supercluster, a vast collection of galaxy groups and clusters centred on the Virgo cluster, which lies about 50 million light-years away. The Virgo cluster itself contains over 1,300 galaxies, including many giant ellipticals far larger than either the Milky Way or Andromeda. Compared to this great metropolitan centre of galaxies, the local group is a quiet rural outpost. In recent years, astronomers have discovered that the Virgo supercluster is itself part of an even larger structure called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains roughly 100,000 galaxies spread across 520 million light-years, all flowing together under the influence of gravity toward a region called the Great Attractor. The local group, the Virgo supercluster, and Laniakea are all part of the cosmic web, that vast network of filaments and voids that constitutes the large-scale structure of the universe. Understanding Andromeda's place within this hierarchy helps us appreciate both its cosmic significance and its intimate connection to our own galaxy. The Milky Way and Andromeda are not just neighbours, but partners in a gravitational dance that has been ongoing for billions of years and will continue for billions more. They are the twin hearts of the local group, the dominant masses around which all the smaller members orbit and evolve. The space between the Milky Way and Andromeda is not entirely empty. Intergalactic space contains a thin medium of gas and dust, along with countless stars that have been ejected from their parent galaxies through gravitational interactions. Some of these intergalactic stars may have originated in the Milky Way or Andromeda and now wander alone through the void, unbound to any galaxy. The intergalactic medium also contains dark matter, the mysterious substance that makes up most of the mass in the universe, but interacts with ordinary matter only through gravity. The distance between our galaxy and Andromeda has not always been the same. As we will explore in a later chapter, these two great spirals are approaching each other, drawn together by their mutual gravitational attraction. The 2.5 million light-years that currently separate them is slowly but steadily decreasing, and in the distant future, the two galaxies will meet and merge. This cosmic collision, which will unfold over billions of years, will transform both galaxies into something entirely new. For now, however, Andromeda remains our distant neighbour, close enough to study in remarkable detail, yet far enough to appear as little more than a fuzzy patch of light to the naked eye. Its position in the autumn sky of the northern hemisphere makes it a favourite target for amateur astronomers, who can observe it with binoculars or small telescopes and contemplate the vast distances and timescales involved. Every photon of light from Andromeda carries information about a galaxy that existed over 2 million years ago, a message from the deep past that continues to arrive night after night. The cosmic address of the Andromeda Galaxy might be written as follows: Local Group, Virgo Supercluster, Laniakea Supercluster, Observable Universe. This address places it within the context of the larger structures known to astronomy, while also emphasizing its intimate connection to our own Milky Way. We are neighbours in the truest sense, sharing a common gravitational environment and destined to share a common future. As you contemplate the vastness of these distances and structures, allow yourself to feel not diminished, but connected. The atoms in your body were forged in the hearts of stars, and those stars were part of galaxies not unlike Andromeda. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these were created through nuclear fusion in stellar cores and scattered into space when those stars died. You are made of star stuff, as Carl Sagan famously observed, and through that material connection, you are linked to every galaxy in the universe. The Andromeda Galaxy, shining softly in the autumn sky, is a reminder of this cosmic heritage. Its light has travelled for over 2 million years to reach your eyes, carrying information about 1 trillion stars and countless worlds we will never visit. Yet in observing it, in knowing something of its nature and history, we participate in the grand human project of understanding the universe. This is a privilege unique to our species, so far as we know, and it connects us to every astronomer who has ever gazed upward in wonder. Chapter 5. The Magnificent Structure of Andromeda. The Andromeda Galaxy is a spiral galaxy of breathtaking scale and beauty, a cosmic pinwheel containing approximately 1 trillion stars spread across a disk roughly 220,000 light-years in diameter. This makes it significantly larger than our own Milky Way, which spans about 100,000 to 180,000 light-years, depending on how one defines its boundaries. Andromeda is, in fact, the largest galaxy in the local group and one of the most massive spiral galaxies in the nearby universe. When astronomers speak of a galaxy's structure, they are referring to the arrangement of its various components. The central bulge, the disk, the spiral arms, the halo, and the various populations of stars, gas and dust that make up each region. Understanding this structure requires observations across the electromagnetic spectrum, from radio waves to gamma rays, each wavelength revealing different aspects of the galaxy's composition and dynamics. The most prominent feature of Andromeda, visible even in small telescopes, is its central bulge. This roughly spherical concentration of stars occupies the innermost region of the galaxy, extending outward for about 10,000 light-years from the centre. The bulge is densely packed with old, reddish stars that formed early in the galaxy's history, giving it a warm, golden glow in colour images. Unlike the disk, which rotates in an organised fashion, the stars in the bulge move on more random orbits, creating a three-dimensional swarm rather than a flat spinning disk. At the very heart of the bulge lies Andromeda's central engine, a supermassive black hole with a mass estimated at 100 to 230 million times that of our Sun. This gravitational monster, while enormous by any human standard, is relatively modest compared to the supermassive black holes found in some other galaxies, which can exceed billions of solar masses. The black hole at the centre of the Milky Way, known as Sagittarius A3, is even smaller, containing only about 4 million solar masses. Andromeda's central black hole is thus 25 to 50 times more massive than our own. Surrounding the central bulge is Andromeda's disk, a flattened structure where most of the galaxy's gas, dust, and ongoing star formation are concentrated. The disk extends outward from the bulge for over 100,000 light-years, though its exact boundaries are difficult to define as it gradually fades into the surrounding halo. Within the disk, stars orbit the galactic centre in roughly circular paths, all moving in the same direction, like cars on a cosmic highway. The most striking feature of the disk is its spiral arm pattern. Andromeda possesses 2 main spiral arms that wind outward from the central regions, along with numerous smaller arm segments and spurs. These arms are not solid structures, but rather density waves, regions where stars, gas and dust are temporarily compressed as they orbit through the disk. The compression triggers star formation, which is why spiral arms appear brighter than the regions between them. They contain more young, luminous stars. The spiral arms of Andromeda are traced by different components, depending on how you observe them. In visible light, the arms stand out because of their young blue stars and the glowing nebulae where new stars are being born. In infrared light, which penetrates dust more easily than visible light, the arms are traced by older, cooler stars that make up the bulk of the stellar population. In radio waves, the arms appear as concentrations of neutral hydrogen gas, the raw material from which new stars form. One of the most distinctive features of Andromeda's disk is a ring of star formation located about 32,000 light-years from the centre. This ring, discovered through infrared observations, contains a high concentration of young stars and star-forming regions. Some astronomers believe the ring was created by a gravitational interaction with one of Andromeda's satellite galaxies, perhaps M32, which may have passed through the disk and triggered a wave of star formation. This interpretation remains debated, but it highlights the dynamic nature of galaxies and the importance of interactions in shaping their structure. Beyond the visible disk lies Andromeda's halo, a roughly spherical region containing old stars, globular clusters, and dark matter. The stellar halo is much less dense than the disk, containing only a small fraction of the galaxy's total stellar mass, but it extends to enormous distances, perhaps 500,000 light-years or more from the centre. The stars in the halo are among the oldest in the galaxy, formed during the earliest stages of Andromeda's assembly from smaller protogalactic fragments. Globular clusters are particularly abundant in Andromeda's halo. These dense, spherical collections of old stars are among the most ancient objects in any galaxy, with ages approaching the age of the universe itself. Andromeda contains approximately 450 known globular clusters, significantly more than the Milky Way's 150 or so. The most massive globular cluster in the local group, known as G1 or Mile 2, belongs to Andromeda. This enormous cluster contains several million stars and may actually be the stripped core of a dwarf galaxy that was absorbed by Andromeda long ago. The dark matter halo of Andromeda is invisible to direct observation, but reveals its presence through its gravitational effects on visible matter. Dark matter is a mysterious substance that does not emit, absorb, or reflect light, yet makes up about 85% of all matter in the universe. Its existence is inferred from the motions of stars and gas in galaxies, which move faster than they should if only visible matter were present. The dark matter halo of Andromeda is estimated to contain about 1.5 trillion solar masses, far exceeding the mass of all the visible stars, gas and dust combined. The extent of Andromeda's dark matter halo has been a subject of recent research and some surprise. Studies of the motions of satellite galaxies and other tracers suggest that the halo extends to at least 1.3 million light-years from the centre, and possibly as far as 2 million light-years. At these distances, the halo of Andromeda may actually overlap with the halo of the Milky Way, meaning that in some sense, the two galaxies are already touching, their dark matter distributions intermingling across the intergalactic void. The gas content of Andromeda is another important aspect of its structure. The galaxy contains substantial amounts of neutral hydrogen, the raw material from which new stars form. This gas is concentrated in the disk, particularly in the spiral arms and the star-forming ring. Observations at radio wavelengths have mapped the distribution of hydrogen throughout the galaxy, revealing a complex structure with warps and distortions that suggest gravitational interactions with satellite galaxies or the intergalactic medium. Dust is also present throughout Andromeda's disk, concentrated in lanes that follow the spiral arms and ring structures. This dust, composed of tiny particles of carbon, silicon, and other elements, absorbs visible light and re-emits it at infrared wavelengths. Dust lanes appear dark in visible light images of Andromeda, creating striking contrast against the bright background of stars. The dust plays an important role in star formation, providing surfaces on which hydrogen molecules can form and helping to cool gas clouds to the temperatures necessary for gravitational collapse. The overall shape of Andromeda as seen from Earth is that of an elongated ellipse tilted about 77 degrees from face-on. This high inclination means we are viewing the galaxy almost edge-on, which compresses its apparent width and makes the spiral arms more difficult to discern than they would be in a face-on view. Despite this unfavourable viewing angle, the spiral structure is clearly visible in photographs, and the dust lanes stand out dramatically against the bright central bulge. If we could somehow travel to a vantage point directly above Andromeda and look down on it face-on, we would see a magnificent spiral pattern, with two main arms winding outward from the centre and numerous smaller features adding complexity to the overall design. The central bulge would appear as a bright yellowish core, surrounded by the bluer disk, with its lanes of dark dust and knots of pink star-forming regions. It would be a view of stunning beauty, one of the grandest sights in the local universe. The rotation of Andromeda has been measured through observations of the Doppler shift in its spectral lines. As the galaxy rotates, one side approaches us while the other recedes, causing the light from these regions to be blue-shifted and red-shifted respectively. These measurements reveal that Andromeda rotates with a period of about 225 million years at the distance of the Sun from the centre of the Milky Way, similar to our own galaxy's rotation period. The outer parts of the disk rotate more slowly than the inner parts, but not as slowly as would be expected if only visible matter were present. This discrepancy is one of the key pieces of evidence for the existence of dark matter. The mass of the Andromeda Galaxy has been estimated through various methods, including the motions of its stars and satellite galaxies, the dynamics of its gas, and gravitational lensing of background objects. Current estimates place the total mass at about 1.5 trillion solar masses, with most of this mass in the form of dark matter. The stellar mass is estimated at about 100 to 150 billion solar masses, while the gas mass adds another 10 billion solar masses or so. These figures make Andromeda one of the most massive spiral galaxies known, though it is surpassed by some giant ellipticals and the central galaxies of rich clusters. Recent research has refined our understanding of Andromeda's mass in comparison to the Milky Way. For many years, it was assumed that Andromeda was significantly more massive than our galaxy, perhaps twice as massive or more. However, more precise measurements have suggested that the two galaxies are more similar in mass than previously thought, with the Milky Way possibly containing more dark matter than earlier estimates indicated. The current consensus is that Andromeda is somewhat more massive in terms of stellar content, but the total masses, including dark matter, are comparable. The structure of Andromeda is not static but constantly evolving. Stars are born in the spiral arms and star-forming ring, live out their lives, and die, returning processed material to the interstellar medium. Gas flows through the disk, compressed by density waves and gravitational interactions. Satellite galaxies orbit and occasionally plunge through the disk, triggering bursts of star formation and leaving streams of debris in their wake. The supermassive black hole at the centre occasionally flares as material falls into it, though Andromeda's nucleus is currently relatively quiet. Over billions of years, these processes have shaped Andromeda into the magnificent spiral we observe today, and over billions of years more, they will continue to reshape it, eventually transforming it entirely when it merges with our own Milky Way. The structure we see now is just a snapshot in the long history of a galaxy that has existed for most of the age of the universe and will continue to exist in one form or another for countless eons to come. Chapter 6: The Stellar Population of Andromeda. Within the vast expanse of the Andromeda Galaxy dwell approximately 1 trillion stars, a number so large that it defies easy comprehension. If you were to count one star per second, it would take you over 31,000 years to count them all, and that assumes you never pause to sleep or eat. This stellar population is not uniform, but varies dramatically from region to region, with different types of stars dominating different parts of the galaxy. The stars of Andromeda, like those of all galaxies, can be divided into populations based on their ages, chemical compositions, and locations within the galaxy. Astronomers traditionally distinguish between population 1 stars, which are young, metal-rich, and found primarily in the disk and spiral arms, and population 2 stars, which are old, metal-poor, and found primarily in the bulge and halo. This classification, while simplified, captures an important truth about galactic structure. Different regions of a galaxy have different histories and contain different types of stars. The term metal in astronomy has a specific meaning that differs from everyday usage. To an astronomer, any element heavier than helium is a metal, including elements like carbon, oxygen, and nitrogen that chemists would classify as non-metals. This unconventional terminology reflects the fact that hydrogen and helium were the only elements created in the Big Bang. All heavier elements were synthesized later in the cores of stars and dispersed into space when those stars died. The metal content of a star thus reflects the chemical enrichment of the gas from which it formed, which in turn reflects the history of previous generations of stars. The oldest stars in Andromeda are found in the halo and the central bulge. These ancient objects formed during the earliest stages of the galaxy's assembly, perhaps 10 to 13 billion years ago, when the universe itself was young. They contain very few metals because the gas from which they formed had not yet been enriched by many generations of stellar nucleosynthesis. Some of these stars may be among the oldest in the universe, witnesses to cosmic epochs long before Earth or the Sun existed. The globular clusters of Andromeda are particularly valuable for studying old stellar populations. These dense spherical collections of stars formed early in the galaxy's history and have remained largely unchanged ever since. By analysing the colours and brightnesses of stars in globular clusters, astronomers can determine their ages and chemical compositions with considerable precision. The globular clusters of Andromeda span a range of ages and metallicities, suggesting that the galaxy assembled over an extended period through the accretion of smaller systems. The most massive globular cluster in the local group, Male 2 or G1, orbits Andromeda at a distance of about 130,000 light-years from the centre. This remarkable object contains several million stars packed into a region only about 100 light-years in diameter. Its mass is estimated at 10 million solar masses, making it more massive than many dwarf galaxies. Some astronomers believe that G1 is not a true globular cluster, but rather the stripped nucleus of a dwarf galaxy that was absorbed by Andromeda long ago. This interpretation is supported by the presence of a central black hole within G1, a feature not typically found in ordinary globular clusters. Moving inward from the halo to the bulge, we encounter a denser concentration of old stars. The bulge of Andromeda contains billions of stars, most of them old and reddish in colour. These stars formed during the early stages of the galaxy's evolution, when gas was still settling into the disk and star formation was occurring throughout a more extended spheroidal distribution. The bulge stars have higher metallicities than the halo stars, reflecting the greater chemical enrichment of the inner regions, where more generations of stars have lived and died. The disk of Andromeda contains a more diverse stellar population, with stars ranging from very old to newly formed. The older disk stars, sometimes called the thick disk population, are several billion years old and have intermediate metallicities. They occupy a thicker, more puffed-up distribution than the younger stars, a result of gravitational heating over time. The younger disk stars, the thin disk population, are more tightly confined to the plane of the galaxy and include the bright blue stars that trace the spiral arms. The spiral arms of Andromeda are the sites of ongoing star formation, where giant molecular clouds collapse under their own gravity to produce new generations of stars. These regions are marked by the presence of hot, luminous blue stars, which are massive and short-lived. A typical blue giant might contain 10 to 50 times the mass of the Sun and shine with 10,000 to 100,000 times the Sun's luminosity, but it will exhaust its nuclear fuel in just a few million years. The presence of such stars in the spiral arms indicates that star formation is actively occurring there today. Surrounding the young blue stars in the spiral arms are emission nebulae, clouds of gas that glow with the characteristic pink light of ionized hydrogen. The ultraviolet radiation from hot young stars strips electrons from hydrogen atoms in these clouds, and when the electrons recombine with protons, they emit light at specific wavelengths, including the distinctive hydrogen alpha line in the red part of the spectrum. These glowing nebulae, often called H2 regions, are stellar nurseries where new stars are being born. One of the most prominent star-forming regions in Andromeda is NGC 206, a giant stellar association located in the southwestern portion of the galaxy's disk. This region contains thousands of young hot stars, along with the gas and dust from which they recently formed. NGC 206 is visible as a bright patch in photographs of Andromeda, and can even be glimpsed in large amateur telescopes under good conditions. It serves as a reminder that Andromeda, despite its great age, is still actively producing new stars. The star-forming ring at 32,000 light-years from Andromeda's centre is another region of intense stellar activity. This ring contains a high concentration of molecular gas and dust, the raw materials for star formation, along with numerous young stellar associations and H2 regions. The origin of this ring is debated, but one possibility is that it was triggered by the passage of a satellite galaxy, perhaps M32, through Andromeda's disk. Such an interaction would compress gas and trigger a wave of star formation, leaving behind the ring structure we observe today. At the other end of the stellar life cycle, Andromeda contains numerous stellar remnants, white dwarfs, neutron stars, and black holes. These are the endpoints of stellar evolution, the remains left behind when stars exhaust their nuclear fuel and die. White dwarfs are the cause of Sun-like stars, compact objects about the size of Earth but with masses comparable to the Sun. Neutron stars are even more extreme, packing a solar mass or more into a sphere just 20 kilometers in diameter. Stellar black holes, formed from the most massive stars, are regions of space where gravity is so strong that nothing, not even light, can escape. These stellar remnants are generally invisible in ordinary observations of Andromeda, but they reveal their presence in various ways. White dwarfs in binary systems can accrete material from their companions and produce nova explosions, sudden brightenings that can be detected even across the vast distance to Andromeda. Neutron stars can appear as pulsars, rapidly spinning objects that emit beams of radio waves, or as X-ray sources when they accrete material from nearby stars. Stellar black holes in binary systems can also produce X-rays as material spirals into them. Andromeda has been the site of one supernova observed from Earth. S Andromeda, which appeared in 1885 and briefly rivaled the entire galaxy in brightness. This event, occurring before the true nature of Andromeda was understood, was initially classified as an ordinary nova. Only later did astronomers realize that it must have been a supernova, an explosive death of a massive star, to be visible at such an enormous distance. S Andromedae is now classified as a Type Ia supernova, the thermonuclear explosion of a white dwarf that has accreted too much material from a companion star. The stellar population of Andromeda also includes various types of variable stars, objects whose brightness changes over time due to pulsations, eclipses, or other physical processes. Cepheid variables, the stars that Edwin Hubble used to measure the distance to Andromeda, are among the most important of these. By identifying and studying Cepheids in Andromeda, astronomers have refined the distance to the galaxy and used it as a stepping stone to measure distances to even more remote objects. Other types of variable stars in Andromeda include Ara Lyrae stars, which are old, low-mass pulsating stars found primarily in the halo and globular clusters. Mira variables, which are cool red giants that pulsate with periods of hundreds of days. And eclipsing binaries, pairs of stars that orbit each other and periodically block each other's light as seen from Earth. Each type of variable star provides different information about the stellar population and the physical conditions within the galaxy. The chemical evolution of Andromeda's stellar population tells the story of the galaxy's history. The oldest, most metal-poor stars in the halo formed from gas that had been enriched by only a few generations of previous stars. As time passed and more stars lived and died, the gas became progressively more enriched with heavy elements. The youngest stars in the disk, formed from gas that has been processed through many stellar generations, have the highest metallicities. This pattern of increasing metallicity with decreasing age is a universal feature of galaxies and reflects the ongoing cycle of stellar birth, death, and chemical enrichment. Comparing the stellar population of Andromeda to that of the Milky Way reveals both similarities and differences. Both galaxies contain old metal-poor stars in their halos and young metal-rich stars in their disks. Both have prominent central bulges dominated by old stars. However, Andromeda's bulge is larger and more massive than the Milky Way's, and its disk contains more stars overall. The star formation rate in Andromeda appears to be somewhat lower than in the Milky Way at present, though this has varied over the galaxy's history. The trillion stars of Andromeda represent a vast diversity of stellar types, ages, and evolutionary stages. From the ancient red giants of the halo to the brilliant blue supergiants of the spiral arms, from the dense cores of globular clusters to the diffuse stellar associations of the disk. This galaxy contains examples of nearly every type of star known to astronomy. Each star has its own history, its own unique set of properties, and potentially its own system of planets. The stellar population of Andromeda is not just a collection of points of light, but a community of suns, each one a potential centre for worlds we can only imagine. Chapter 7: Andromeda's Family of Satellite Galaxies. No great galaxy exists in isolation. Just as planets orbit stars and moons orbit planets, smaller galaxies orbit larger ones, bound by gravity into hierarchical systems that span hundreds of thousands of light years. The Andromeda Galaxy, as the largest member of the local group, possesses an extensive family of satellite galaxies, small stellar systems that have been captured by its gravitational influence and now accompany it on its journey through the cosmos. The satellite galaxies of Andromeda are diverse in their properties, ranging from relatively bright objects visible in amateur telescopes to ultra-faint dwarfs. that challenge the detection limits of the largest professional instruments. As of current counts, astronomers have identified at least 35 satellite galaxies orbiting Andromeda, though new discoveries continue to be made as survey techniques improve. The true number may be considerably higher, with many small faint satellites remaining undetected against the background of more distant galaxies and foreground stars. The two most prominent satellites of Andromeda are M32 and M110, both of which are visible in the same telescopic field of view as the main galaxy. These companions have been known since the 18th century and were catalogued by Charles Messier along with the Great Galaxy itself. They represent two different types of dwarf galaxies. M32 is a compact elliptical, while M110 is a dwarf elliptical with a more extended diffuse structure. M32, also designated NGC 221, is one of the most unusual galaxies in the local group. Despite its small size, spanning only about 6,500 light-years in diameter, it is remarkably dense, containing several billion stars packed into a compact, nearly spherical volume. At its centre lies a supermassive black hole estimated at 1.5 to 5 million solar masses, an unexpectedly massive object for such a small galaxy. The stellar population of M32 is dominated by old metal-rich stars, giving it a yellowish colour in photographs. The compact nature of M32 has led many astronomers to conclude that it was once a much larger galaxy, perhaps a small spiral or a more extended elliptical, that has been dramatically transformed by its interactions with Andromeda. As M32 orbited through the disk and halo of its giant neighbour, tidal forces stripped away its outer stars, leaving only the dense central core. This process, known as tidal stripping, is a common fate for satellite galaxies that venture too close to their hosts. Evidence for this transformation comes from several sources. The stellar population of M32 is unusually metal-rich for a dwarf galaxy, suggesting that it once had a more extended history of star formation and chemical enrichment than its current small size would suggest. The presence of a supermassive black hole at its centre is another clue, as black holes of this mass are typically found in much larger galaxies. If M32 was once a more substantial system, its central black hole would be a natural remnant of that earlier, grander existence. Some astronomers have proposed that M32 may have been responsible for creating the ring of star formation observed in Andromeda's disk. According to this scenario, M32 passed directly through the disk of Andromeda sometime in the past few 100 million years, triggering a wave of compression that propagated outward and stimulated the formation of new stars. This head-on collision would also have stripped away much of M32's outer material, contributing to its current compact state. While this hypothesis remains debated, it illustrates the dynamic nature of galaxy interactions and the profound effects that satellites can have on their host galaxies. M110, the other prominent satellite of Andromeda, presents a very different picture. This dwarf elliptical galaxy is larger and more diffuse than M32, spanning about 17,000 light-years and containing an estimated 10 billion stars. Unlike M32, M110 shows evidence of recent star formation, with young blue stars visible in its central regions. This is unusual for an elliptical galaxy, which are typically composed entirely of old stars and lack the gas necessary for new star formation. The presence of young stars in M110 suggests that this galaxy has retained some of its interstellar gas despite its interactions with Andromeda, or that it has recently acquired new material through some process not fully understood. One possibility is that M110 has captured gas from the intergalactic medium or from streams of material stripped from other satellites. Another is that its orbit has kept it relatively far from Andromeda's disk, protecting it from the intense tidal forces that have transformed M32. M110 also contains a system of dust lanes visible in deep images, another feature unusual for an elliptical galaxy. These dust lanes suggest the presence of interstellar material that could fuel future star formation. The galaxy's structure shows some irregularities that may indicate past interactions or ongoing tidal disturbance. Overall, M110 appears to be a galaxy in transition, neither a pristine elliptical nor an actively star-forming system, but something in between. Beyond M32 and M110, Andromeda's satellite system includes numerous smaller dwarf galaxies that require larger telescopes to observe. These satellites fall into several categories based on their structures and stellar populations. Dwarf spheroidal galaxies are the most common type, characterized by their roughly spherical shapes, low surface brightnesses, and predominantly old stellar populations. Dwarf irregular galaxies have more chaotic structures and often contain ongoing star formation. Dwarf elliptical galaxies like M110 have smooth, regular shapes but vary widely in their sizes and stellar contents. Among the dwarf spheroidal satellites of Andromeda, several have been studied in considerable detail. Andromeda 1, discovered in 1970, was one of the first faint satellites to be identified. It lies about 180,000 light-years from Andromeda's centre and contains only a few million stars. Its stellar population is predominantly old and metal-poor, similar to the globular clusters and halo stars of the Milky Way. Andromeda 1 represents a typical example of the small, faint satellites that populate the outer regions of large galaxies. Andromeda 2, discovered in 1970, along with Andromeda 1, is another dwarf spheroidal satellite located about 185,000 light-years from Andromeda's centre. This small galaxy has a similar stellar population to Andromeda 1, dominated by old metal-poor stars. Studies of its structure have revealed some evidence for tidal disturbance, suggesting that it has been affected by Andromeda's gravitational influence, even at this relatively large distance. The discovery of new satellite galaxies around Andromeda has accelerated dramatically in recent decades, thanks to large-scale surveys that systematically search for faint, diffuse stellar systems. The Sloan Digital Sky Survey and the Pan-STARRS survey have been particularly productive, identifying numerous previously unknown satellites of both Andromeda and the Milky Way. These discoveries have revealed that the satellite populations of large galaxies are far more extensive than earlier observations had suggested. One of the most intriguing discoveries has been the existence of a thin plane of satellite galaxies around Andromeda. Many of the satellites, rather than being distributed randomly in 3 dimensions, appear to lie within a flattened structure that is roughly perpendicular to Andromeda's disk. This plane of satellites extends for hundreds of thousands of light-years and contains a significant fraction of the known companions. The satellites within this plane also appear to be rotating coherently, orbiting Andromeda in the same direction. The existence of this satellite plane has generated considerable scientific interest and some controversy. Standard models of galaxy formation, based on the behaviour of dark matter in cosmological simulations, predict that satellite galaxies should be distributed roughly spherically around their hosts, not concentrated in thin planes. The observed planar structure around Andromeda, along with a similar structure around the Milky Way, has led some researchers to question aspects of the standard cosmological model. Various explanations have been proposed for the satellite planes. One possibility is that the satellites form together from a common structure, perhaps a filament of material falling into the local group from the cosmic web. Another is that the planes represent the debris of ancient galaxy collisions, with the satellites being fragments of larger systems that were disrupted long ago. A third possibility is that the standard cosmological model is incomplete, and that some modification to our understanding of dark matter or gravity is required. The debate continues, and the satellite planes remain an active area of research. The satellite galaxies of Andromeda are not merely passive companions, but active participants in the evolution of the larger system. As they orbit through Andromeda's halo, they experience tidal forces that can strip away their outer stars and gas. This stripped material forms streams and shells that gradually merge with Andromeda's halo, contributing to its growth over time. The process of satellite accretion is one of the primary mechanisms by which large galaxies grow, and evidence for past accretion events can be found throughout Andromeda's structure. One of the most dramatic examples of satellite accretion in progress is the giant stellar stream, a vast ribbon of stars that wraps around Andromeda's halo. This stream was discovered in 2001 through careful mapping of the galaxy's outer regions, and is believed to be the debris of a dwarf galaxy that fell into Andromeda and was torn apart by tidal forces. The stream contains millions of stars spread across hundreds of thousands of light years, a ghostly remnant of a galaxy that no longer exists as a coherent system. The giant stellar stream provides a window into Andromeda's recent history of satellite accretion. By studying the properties of the stars in the stream, their ages, chemical compositions and velocities, astronomers can reconstruct the properties of the progenitor galaxy and the orbit it followed before being disrupted. This information helps constrain models of galaxy formation and the distribution of dark matter in Andromeda's halo. Other streams and substructures have been discovered in Andromeda's halo, each representing the debris of a past accretion event. The halo is not a smooth uniform distribution of stars, but a complex patchwork of overlapping streams, shells, and clouds, each with its own distinct properties. This complexity reflects the hierarchical nature of galaxy formation, in which large galaxies are built up over billions of years through the accretion of smaller systems. The satellite galaxies of Andromeda also provide valuable laboratories for studying dark matter. Dwarf galaxies are believed to be among the most dark matter-dominated systems in the universe, with dark matter making up 90% or more of their total mass in some cases. By measuring the motions of stars within these small galaxies, astronomers can infer the distribution of dark matter and test predictions of cosmological models. Studies of Andromeda's satellites have yielded some surprising results. Some dwarf galaxies appear to contain less dark matter than expected, while others seem to have dark matter distributions that differ from theoretical predictions. These discrepancies have fueled ongoing debates about the nature of dark matter and the processes that shape dwarf galaxies. Whether they indicate problems with the standard cosmological model or simply reflect the complex physics of galaxy formation remains an open question. The future of Andromeda's satellite system is tied to the future of the local group as a whole. As Andromeda and the Milky Way approach each other and eventually merge, their satellite systems will be profoundly affected. Some satellites may be ejected from the merged system entirely, flung outward by gravitational interactions during the collision. Others will be absorbed into the growing central galaxy, their stars and dark matter becoming part of the larger whole. The satellite planes, if they survive the merger at all, will likely be disrupted and dispersed. For now, however, the satellite galaxies of Andromeda continue their ancient orbits, small worlds circling a larger one in a gravitational dance that has continued for billions of years. Each satellite has its own history, its own population of stars, and potentially its own system of even smaller companions. Together, they form a family of galaxies bound by gravity and shared destiny, a microcosm of the larger structures that fill the universe. Chapter 8: The Supermassive Heart of Andromeda. At the very centre of the Andromeda Galaxy, hidden within the dense concentration of stars that forms the galactic bulge, lies one of the most extraordinary objects in the local universe. A supermassive black hole with a mass between 100 million and 230 million times that of our Sun. This gravitational behemoth, though invisible to direct observation, exerts a profound influence on its surroundings and holds clues to the history and evolution of the galaxy itself. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape once it crosses the boundary known as the event horizon. They are predicted by Einstein's general theory of relativity, which describes gravity as the curvature of spacetime caused by mass and energy. When enough mass is concentrated into a small enough volume, the curvature becomes so extreme that spacetime effectively closes in on itself, creating a one-way boundary from which there is no return. Supermassive black holes, like the one at Andromeda's centre, are distinguished from their smaller cousins by their enormous masses. While stellar black holes formed from the collapse of massive stars typically contain between 5 and 50 solar masses, supermassive black holes range from millions to billions of solar masses. They are found at the centres of most, perhaps all, large galaxies, and their masses are correlated with the properties of their host galaxies in ways that suggest a deep connection between black hole growth and galaxy evolution. The supermassive black hole at the centre of Andromeda, sometimes designated as M3 Ralt, is among the most massive known in the local universe. Its mass has been estimated through several methods, all of which rely on observing the motions of stars and gas near the galactic centre. Stars that orbit close to the black hole move faster than those farther away, and by measuring these velocities, astronomers can infer the mass of the central object. One of the most precise measurements of M32's mass comes from observations with the Hubble Space Telescope, which can resolve individual stars in Andromeda's central region despite the galaxy's great distance. These observations revealed that stars within a few light years of the centre are moving at velocities of several hundred kilometres per second, far faster than would be expected if only the visible stars were providing the gravitational attraction. The implied mass of the central object, concentrated into a region smaller than the solar system, can only be explained by a supermassive black hole. The environment immediately surrounding M31 is complex and dynamic. Unlike some supermassive black holes, which are surrounded by brilliant accretion disks of infalling material and produce powerful jets of radiation, Andromeda's central black hole is relatively quiescent. It is not actively consuming large amounts of gas and dust, and it does not produce the intense radiation characteristic of active galactic nuclei. This quiet state reflects the current conditions in Andromeda's centre, where the supply of material available for the black hole to consume is limited. However, the region around M31 is not entirely inactive. Observations at X-ray wavelengths have detected emission from hot gas near the black hole, indicating that some material is falling inward and being heated to extreme temperatures. The X-ray luminosity of Andromeda's nucleus is modest compared to active galaxies, but it confirms that the black hole is not completely dormant. Occasional flares have been observed, suggesting episodes of enhanced accretion when larger clumps of material approach the event horizon. One of the most intriguing features of Andromeda's central region is the presence of a double nucleus, two distinct concentrations of light, separated by only a few light years. This structure, discovered in the 1990s through high-resolution observations, initially puzzled astronomers. Was Andromeda home to two supermassive black holes, perhaps the remnants of a past galaxy merger? Or was there some other explanation for the double peak in the light distribution? The currently accepted explanation for the double nucleus involves a disk of stars orbiting the supermassive black hole on eccentric, elongated paths. In this model, the brighter of the two peaks corresponds to a region where stars spend more time due to their slower velocities at the far points of their orbits, while the fainter peak marks the location of the black hole itself, where stars move fastest and spend less time. This eccentric disk may have formed through a past interaction, perhaps the infall of a smaller galaxy or a dense star cluster into Andromeda's centre. The double nucleus provides a unique laboratory for studying the dynamics of stars in extreme gravitational environments. The stars in this region are subject to intense tidal forces and frequent close encounters with each other and with the black hole. Some stars may be torn apart by tidal forces if they approach too close to the event horizon, producing brief flares of radiation as their material is consumed. Others may be ejected from the nucleus entirely, flung outward at high velocities by gravitational interactions. The supermassive black hole at Andromeda's centre did not always exist in its current form. Like all supermassive black holes, it grew over billions of years through the accretion of gas and the mergers of smaller black holes. The seeds of supermassive black holes may have been stellar mass black holes formed from the first generation of stars in the early universe, or they may have been more massive objects that formed directly from the collapse of primordial gas clouds. The exact mechanism by which supermassive black holes form and grow remains an active area of research. Throughout Andromeda's history, its central black hole has likely experienced periods of intense activity interspersed with longer quiet phases like the present, when large amounts of gas were available, perhaps during galaxy mergers or periods of intense star formation. The black hole would have accreted material rapidly and shone as an active galactic nucleus or quasar. These active phases would have produced enormous amounts of radiation and may have driven powerful outflows that affected the entire galaxy. The relationship between supermassive black holes and their host galaxies is one of the most important topics in modern astrophysics. Observations have revealed tight correlations between black hole mass and various properties of the host galaxy, including the mass of the central bulge and the velocities of stars in the bulge. These correlations suggest that black holes and galaxies grow together, with feedback processes linking the two. In the feedback scenario, energy released by the accreting black hole heats and expels gas from the galaxy, regulating star formation and limiting the growth of both the black hole and the galaxy. When the black hole accretes rapidly, it produces intense radiation and outflows that push gas away from the centre, cutting off the fuel supply and causing the black hole to become quiescent. As gas gradually accumulates again, the cycle repeats. This self-regulating process may explain why black hole masses are correlated with galaxy properties and why most large galaxies have similar ratios of black hole mass to bulge mass. Andromeda's supermassive black hole, with its mass of 100 to 230 million solar masses, fits reasonably well into these correlations. Given the mass of Andromeda's bulge, a black hole of this size is approximately what would be expected. The Milky Way's central black hole, Sagittarius A Heights, is considerably smaller at about 4 million solar masses, reflecting the smaller bulge of our galaxy. When the two galaxies eventually merge, their central black holes will also merge, creating an even more massive object at the centre of the combined system. The process by which supermassive black holes merge is complex and not fully understood. When two galaxies collide, their central black holes do not immediately find each other. Instead, they sink toward the centre of the merged system through a process called dynamical friction, in which gravitational interactions with surrounding stars gradually drain their orbital energy. This process can take hundreds of millions or even billions of years, depending on the properties of the merging galaxies. Once the two black holes approach within a few light years of each other, they form a binary system orbiting their common center of mass. The binary continues to lose energy through interactions with nearby stars, gradually shrinking its orbit. In the final stages, the black holes emit gravitational waves, ripples in space-time predicted by general relativity, which carry away the remaining energy and cause the black holes to spiral together and merge. The final merger produces a burst of gravitational waves that, for the most massive black holes, would be detectable across the universe. The merger of the Milky Way and Andromeda's supermassive black holes lies billions of years in the future, but it is a virtually certain outcome of the galaxy's collision. The merged black hole will have a mass of at least 100 million solar masses, and possibly much more if significant accretion occurs during the merger process. This object will anchor the center of the new galaxy that forms from the collision, continuing the cycle of growth and evolution that has characterized supermassive black holes throughout cosmic history. For now, Andromeda's supermassive black hole sits quietly at the galaxy's heart, a sleeping giant that has shaped the evolution of its host galaxy and will play a central role in its future. Though invisible to our telescopes, its presence is felt through the motions of nearby stars and the structure of the galactic center. It is a reminder that even the most serene-looking galaxies harbor objects of extraordinary power, engines capable of outshining entire galaxies when awakened from their slumber. Chapter 9. The Dark Matter Enigma. Surrounding the visible splendor of the Andromeda Galaxy, extending far beyond the reach of its outermost stars, lies an invisible realm of profound mystery. This is the domain of dark matter, a substance that makes up the majority of Andromeda's mass, yet remains undetectable by any form of light or electromagnetic radiation. The dark matter halo of Andromeda is one of the largest structures in the local group, a vast, roughly spherical distribution of matter that shapes the galaxy's dynamics and holds the key to understanding its past and future. Dark matter earned its name because it does not emit, absorb, or reflect light. It is invisible to telescopes operating at any wavelength, from radio waves to gamma rays. Yet astronomers are confident that dark matter exists because of its gravitational effects on visible matter. Stars and gas in galaxies move faster than they should if only visible matter were present, and the only explanation that fits all the observations is that galaxies are embedded in massive halos of unseen material. The evidence for dark matter in Andromeda comes from several sources. The most direct is the rotation curve of the galaxy, a plot of how fast stars and gas orbit at different distances from the center. If only visible matter were present, the rotation speed would decrease with distance from the center, following the same pattern as planets orbiting the Sun. Instead, the rotation curve of Andromeda remains roughly flat out to large distances, indicating that the gravitational pull does not diminish as expected. This flat rotation curve implies the presence of additional mass extending far beyond the visible disk, a dark matter halo. The motions of Andromeda's satellite galaxies provide another probe of the dark matter distribution. Satellites orbit within the gravitational potential of the halo, and their velocities depend on the total mass enclosed within their orbits. By measuring the velocities of many satellites at different distances, astronomers can map out the mass distribution of the halo. These studies indicate that Andromeda's dark matter halo extends to at least 1.3 million light-years from the center, and possibly as far as 2 million light-years. The total mass of Andromeda's dark matter halo is estimated at approximately 1.5 trillion solar masses, though this figure carries considerable uncertainty. This mass is about 10 times greater than the mass of all the visible stars, gas and dust in the galaxy combined. In other words, the beautiful spiral that we observe in photographs represents only a small fraction of Andromeda's total mass. The vast majority is invisible dark matter. The nature of dark matter remains one of the greatest unsolved problems in physics. Despite decades of research, scientists have not yet identified what dark matter is made of. The leading hypothesis is that dark matter consists of some type of elementary particle that interacts with ordinary matter only through gravity and possibly the weak nuclear force. These hypothetical particles, often called WIMPs, weakly interacting massive particles, would have been produced in the early universe and would still pervade the cosmos today. Numerous experiments around the world are searching for direct evidence of dark matter particles. These experiments typically involve large sensitive detectors placed deep underground to shield them from cosmic rays and other background radiation. The hope is that, occasionally, a dark matter particle will collide with an atom in the detector, producing a tiny signal that can be measured. So far, no definitive detection has been made, but the search continues with increasingly sensitive instruments. Other candidates for dark matter include axions, hypothetical particles originally proposed to solve a problem in particle physics unrelated to cosmology, and primordial black holes that might have formed in the very early universe, before the first stars. Each candidate has its own predicted properties and signatures, and astronomers and physicists are pursuing multiple lines of investigation to determine which, if any, is correct. Whatever dark matter is made of, its distribution in Andromeda follows certain patterns predicted by cosmological simulations. These simulations, which model the evolution of the universe from shortly after the Big Bang to the present day, show that dark matter forms hierarchical structures, with small clumps merging to form larger ones over time. The dark matter halos of galaxies like Andromeda are not smooth, but contain substructure, smaller clumps and streams that reflect the history of past mergers and accretion events. The substructure in Andromeda's dark matter halo may be detectable through its effects on visible matter. Dark matter clumps can gravitationally lens background objects, bending and magnifying their light in characteristic ways. They can also perturb the orbits of stars and satellite galaxies, creating observable signatures in their motions. Searches for these effects are ongoing, and any detection would provide valuable information about the small-scale distribution of dark matter. One of the most surprising recent discoveries about Andromeda's dark matter halo is its enormous extent. Studies using various tracers, including satellite galaxies, globular clusters, and planetary nebulae, suggest that the halo extends far beyond the visible galaxy, possibly reaching halfway to the Milky Way. If this is correct, then the dark matter halos of Andromeda and the Milky Way may already be overlapping, their outer regions intermingling across the intergalactic void. This overlap has profound implications for the future interaction of the two galaxies. As they approach each other, their dark matter halos will merge first, creating a common envelope of invisible matter within which the visible galaxies will eventually collide. The dynamics of this merger will be dominated by dark matter, which contains most of the mass, even though the spectacular visible effects will involve stars, gas and dust. The dark matter halo also plays a crucial role in the formation and evolution of Andromeda's satellite galaxies. Dwarf galaxies are believed to form within smaller dark matter halos, which then fall into the larger halo of a galaxy like Andromeda. As they orbit within the larger halo, they are subject to tidal forces that can strip away their outer dark matter and stars. The survival of satellite galaxies depends on the density of their dark matter cores. With denser satellites, better able to resist tidal disruption. Studies of Andromeda's satellites have revealed some puzzling features that may relate to dark matter. Some satellites appear to have less dark matter than expected, based on their stellar content and the predictions of cosmological simulations. Others have dark matter distributions that differ from theoretical models, with cores that are less dense than predicted. These discrepancies, sometimes called the small-scale crisis of cosmology, have prompted various explanations. From modifications to the properties of dark matter to complex baryonic processes that can alter dark matter distributions. One proposed solution involves the effects of star formation and supernovae on dark matter halos. When stars form and explode as supernova, they inject energy into the surrounding gas, which can be expelled from the galaxy. This rapid removal of mass can cause the dark matter distribution to expand and become less concentrated, potentially explaining the observed cores in dwarf galaxies. Whether this mechanism can fully account for the observations remains debated. Another possibility is that dark matter is not cold, as assumed in the standard cosmological model, but has some small amount of thermal motion or self-interaction. Warm dark matter or self-interacting dark matter would behave differently on small scales, potentially producing less substructure and less concentrated halos. These alternative dark matter models make specific predictions that can be tested through observations of galaxies like Andromeda and their satellites. The study of dark matter in Andromeda is intimately connected to broader questions about the nature of the universe. Dark matter makes up about 27% of the total energy density of the cosmos, far more than ordinary matter, which accounts for only about 5%. The remaining 68% is dark energy, an even more mysterious component that is causing the expansion of the universe to accelerate. Together, dark matter and dark energy constitute 95% of the universe, yet we understand neither of them at a fundamental level. Andromeda, as one of the nearest large galaxies, provides an invaluable laboratory for studying dark matter. Its proximity allows detailed observations that are impossible for more distant galaxies, while its size ensures that it contains a substantial dark matter halo with measurable effects on visible matter. Every new observation of Andromeda's dynamics, satellite system, or stellar streams adds to our understanding of dark matter and brings us closer to solving one of the greatest mysteries in science. As you contemplate the Andromeda Galaxy, remember that what you see is only a fraction of what is truly there. The beautiful spiral of stars, the glowing nebula, the satellite companions, all of these are embedded within a vast, invisible structure that outweighs them by a factor of 10 or more. Dark matter is the hidden scaffolding of the universe, the unseen framework upon which galaxies are built. In Andromeda, as in our own Milky Way, this invisible majority shapes everything we observe, a silent partner in the cosmic dance of gravity and light. Chapter 10. The Inevitable Collision. Among the most remarkable facts about the Andromeda Galaxy is that it is heading directly toward us. Unlike nearly every other galaxy in the observable universe, which is receding from the Milky Way as space itself expands, Andromeda is approaching at a speed of approximately 110 kilometers per second. This motion, first detected through the blue shift of Andromeda's spectral lines, heralds a cosmic event of staggering proportions, the eventual collision and merger of the two largest galaxies in the local group. The approach of Andromeda toward the Milky Way is not a violation of the expansion of the universe, but rather a consequence of local gravitational attraction overcoming the general cosmic expansion. On the largest scales, galaxies are indeed moving apart as space expands, a phenomenon first discovered by Edwin Hubble in the 1920s. But on smaller scales within galaxy groups and clusters, gravity can bind objects together and cause them to approach each other. The Milky Way and Andromeda, as the dominant members of the local group, are gravitationally bound and have been falling toward each other since the group formed billions of years ago. The collision between the Milky Way and Andromeda is not a possibility but a certainty, barring some unforeseen cosmic intervention. Current estimates place the first close encounter approximately 4 to 5 billion years in the future, though the exact timing depends on details of the galaxy's orbits that are still being refined. The merger process, once begun, will take several billion years more to complete, as the two galaxies interact, separate, and interact again before finally settling into a single combined system. The nature of this collision will be unlike anything in everyday human experience. When we think of collisions, we typically imagine violent impacts, cars crashing, billiard balls striking each other, meteors slamming into planets. But a galaxy collision is fundamentally different. Despite containing hundreds of billions of stars each, the Milky Way and Andromeda are so vast and their stars so widely separated that the probability of any two stars actually colliding is vanishingly small. The collision will be more like two swarms of bees passing through each other than two solid objects striking. To understand why stellar collisions are so rare, consider the scale involved. The average distance between stars in the disk of a galaxy, like the Milky Way, is about 4 to 5 light years. A light year is approximately 9.5 trillion kilometers, an almost incomprehensible distance. Stars themselves are tiny compared to these separations. The Sun, a fairly typical star, has a diameter of only about 1.4 million kilometers. The ratio of stellar size to stellar separation is roughly equivalent to a few grains of sand separated by kilometers of empty space. When two such sparse distributions pass through each other, the grains almost never touch. While individual stars will rarely collide, the gravitational effects of the merger will be dramatic and far-reaching. As the galaxies approach, tidal forces will begin to distort their shapes, pulling streams of stars outward and creating spectacular bridges and tails of material. The beautiful spiral structures of both galaxies will be disrupted and eventually destroyed, their orderly rotation giving way to chaotic motions as stars respond to the rapidly changing gravitational field. Computer simulations of the Milky Way-Andromeda collision, based on our best understanding of the galaxy's masses, structures, and orbits, provide a preview of what is to come. These simulations show that the first close passage will be particularly dramatic, with both galaxies experiencing intense tidal distortion. Long streamers of stars will be flung outward, some extending hundreds of thousands of light years into intergalactic space. The cores of the galaxies will pass close to each other, but not immediately merge, instead swinging past and separating before falling back together. After the first close passage, the galaxies will move apart briefly before their mutual gravity pulls them back for a second encounter. This process will repeat several times over the course of 1 to 2 billion years, with each passage bringing the cores closer together and dissipating more of their orbital energy. Eventually, the two galaxies will merge completely, their stars mixing together to form a single, larger system. The final product of this merger will likely be an elliptical galaxy, a smooth, roughly spherical collection of stars lacking the spiral arms and disk structure of the progenitor galaxies. This is the typical outcome when two large spiral galaxies merge, as the violent gravitational interactions destroy the organized rotation that maintains spiral structure. The new galaxy, sometimes nicknamed Milkomeda or Milkdromeda in popular accounts, will be one of the largest galaxies in the local universe, containing the combined stellar populations of both parent systems. The supermassive black holes at the centers of the Milky Way and Andromeda will eventually merge as well, though this process will take longer than the merger of the stellar populations. As discussed in an earlier chapter, the black holes will first sink toward the center of the merged galaxy through dynamical friction, then form a binary system, and finally spiral together while emitting gravitational waves. The merged black hole will have a mass of at least 100 million solar masses, anchoring the center of the new elliptical galaxy. What will the collision mean for any beings who might be alive in the Milky Way at that distant time? The most important point is that the merger poses no direct threat to planetary systems. As noted above, stellar collisions will be extremely rare, and the vast majority of stars will pass through the merger without any close encounters. The Sun, if it still exists at that time, will likely be carried along in the general flow of stars, its planets continuing to orbit much as they do today. However, the Sun itself will have changed dramatically by the time the collision occurs. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to evolve into a red giant, expanding to perhaps 100 times its current diameter and engulfing the inner planets, including Earth. By the time the Milky Way and Andromeda collide, Earth will likely have been rendered uninhabitable or destroyed entirely, not by the collision but by the natural evolution of our own star. If descendants of humanity, or other intelligent beings, exist at the time of the merger, they will witness a spectacle unlike anything visible from Earth today. The night sky will be transformed as Andromeda grows larger and larger, eventually filling a substantial portion of the visible sky. During the close passages, the sky will blaze with the combined light of 2 trillion stars, and the distorted shapes of the merging galaxies will create patterns of breathtaking beauty. It will be a slow-motion catastrophe, unfolding over millions of years, far too gradual for any single generation to perceive, but recorded in the changing positions of stars over time. The gas in both galaxies will behave differently from the stars during the merger. While stars pass through each other without colliding, gas clouds can collide and interact, compressing and heating as they slam together. This compression will trigger intense bursts of star formation as dense regions of gas collapse under their own gravity to form new stars. The merger will likely produce a starburst phase, during which the rate of star formation will be many times higher than in either galaxy today. Some of the gas may be funneled toward the center of the merging system, where it could feed the supermassive black holes and trigger a period of active galactic nucleus activity. If enough gas reaches the central black holes, they could briefly shine as quasars, producing more light than all the stars in the galaxy combined. This active phase would be visible across the universe, a beacon marking the violent transformation of 2 spiral galaxies into one elliptical. The satellite galaxies of both the Milky Way and Andromeda will be profoundly affected by the merger. Some will be flung outward into intergalactic space, ejected by gravitational interactions during the chaotic merger process. These ejected satellites will become isolated wanderers, small galaxies drifting alone through the void, no longer bound to any larger system. Others will be drawn inward and absorbed into the growing central galaxy, their stars and dark matter becoming part of the merged system. The Magellanic Clouds, the Sagittarius Dwarf, M32, M110, and dozens of other small companions will all face one of these fates. The Triangulum Galaxy, the third largest member of the local group, presents an interesting case. Current observations suggest that Triangulum may be gravitationally bound to Andromeda, orbiting it as a distant satellite. If so, it will be swept up in the merger process along with the smaller companions. Alternatively, Triangulum may be on its first approach to the local group and could be ejected during the Milky Way Andromeda collision. Its ultimate fate depends on details of its orbit that are not yet precisely known. The merger will also affect the intergalactic medium of the local group, the thin gas that fills the space between galaxies. This gas will be compressed and heated by shock waves generated during the collision, potentially reaching temperatures of millions of degrees. Some of this hot gas will eventually cool and fall back into the merged galaxy, providing fuel for future star formation. Other portions may be expelled entirely, enriching the surrounding intergalactic space with heavy elements produced by stars in the merging galaxies. Throughout the merger process, which will span several billion years from first approach to final coalescence, the night sky visible from any planet in either galaxy will undergo continuous transformation. The familiar constellations, already changed beyond recognition by the proper motions of stars over such vast timescales, will be further disrupted as the gravitational tides of the merger rearrange stellar positions. New patterns will emerge, persist for millions of years, and then dissolve as the merger continues. It will be a sky in constant, slow motion, a celestial kaleidoscope turning over geological time. The energy released during the merger will be enormous by any standard. Gravitational potential energy, stored in the separation of the two galaxies, will be converted into kinetic energy of stellar motions, heat in the gas, and radiation from star formation and black hole activity. The total energy involved is difficult to comprehend, equivalent to the output of trillions of suns over billions of years. Yet this energy will be released gradually, spread across such vast volumes of space and time that it poses no threat to any individual star or planet. When the merger is finally complete, perhaps 7 to 10 billion years from now, the result will be a galaxy very different from either of its progenitors. The graceful spiral arms of the Milky Way and Andromeda will be gone, replaced by the smooth, featureless glow of an elliptical galaxy. The organized rotation of the disks will have been converted into random stellar motions, with stars orbiting the center on elongated, inclined paths rather than circular ones. The new galaxy will be larger and more massive than either parent, a giant elliptical dominating the local group. This elliptical galaxy will continue to evolve over the eons that follow. Star formation will gradually decline as the available gas is consumed or expelled. The stellar population will age, with massive blue stars dying off and leaving behind a population dominated by long-lived red dwarfs and the cooling remnants of dead stars. The galaxy will slowly fade and redden, becoming what astronomers call red and dead, a common fate for elliptical galaxies. The supermassive black hole at the center of the merged galaxy will also evolve. After the intense activity that may accompany the merger, it will settle into a quiescent state as the supply of infalling gas diminishes. Over trillions of years, it will slowly evaporate through the quantum mechanical process known as Hawking radiation, though this timescale is so long that the black hole will effectively persist forever on any human or even cosmic scale. The collision between the Milky Way and Andromeda is not an unusual event in the history of the universe. Galaxy mergers have been occurring since the first galaxies formed, and they continue today throughout the cosmos. Observations of distant galaxies reveal many systems in various stages of collision and merger, their distorted shapes and tidal tails providing snapshots of the process. The Milky Way itself bears the scars of past mergers, with streams of stars in its halo tracing the orbits of smaller galaxies that were absorbed long ago. What makes the Milky Way-Andromeda collision special is not its cosmic significance, but its personal relevance. This is our galaxy, the stellar city that contains our sun and our planet, and Andromeda is our nearest large neighbour. The collision will transform the cosmic environment that has been home to Earth and humanity, even though Earth itself will likely be long gone by the time it occurs. There is something poignant about contemplating this distant future, knowing that the familiar sky we see tonight is temporary, a snapshot in an ever-changing cosmic panorama. For now, Andromeda continues its approach, closing the distance between us at 110 kilometers every second. That may sound fast, but at this rate, it will take over 4 billion years for the galaxies to meet. The light we see from Andromeda tonight left the galaxy over 2.5 million years ago, when our ancestors were just beginning to walk upright on the African savanna. By the time the collision occurs, another 4 billion years of evolution will have passed, and whatever beings exist then will be as different from us as we are from the first single-celled organisms that appeared on Earth. The story of the Milky Way Andromeda collision is ultimately a story about change and continuity. The galaxies will change, merging into something new and different. But the stars will continue to shine, planets will continue to orbit, and the fundamental processes of physics will continue to operate as they always have. The universe is not static but dynamic, constantly evolving on timescales that dwarf human history. The collision is simply one more chapter in this ongoing cosmic story, a transformation that will create new possibilities even as it ends old ones. Chapter 11. Modern Discoveries and Continuing Mysteries. The study of the Andromeda Galaxy has entered a golden age in recent decades, as new telescopes and observational techniques have revealed details that were previously invisible or unknown. From space-based observatories peering at wavelengths blocked by Earth's atmosphere, to ground-based surveys mapping millions of individual stars, modern astronomy has transformed our understanding of our nearest large galactic neighbour. Yet even as answers emerge, new questions arise, and Andromeda continues to hold mysteries that challenge our understanding of galaxies and the universe. One of the most significant advances in Andromeda research has come from the Hubble Space Telescope, which has observed the galaxy extensively since its launch in 1990. Hubble's sharp vision, unblurred by Earth's atmosphere, has allowed astronomers to resolve individual stars in Andromeda with unprecedented clarity. The panchromatic Hubble Andromeda Treasury, or FAT, survey mapped over 100 million stars in the galaxy's disk, creating the most detailed census of a galaxy's stellar population ever achieved outside the Milky Way. The PAT survey revealed the complex history of star formation in Andromeda's disk, showing how different regions have experienced bursts and lulls of stellar birth over billions of years. The data allowed astronomers to trace the spiral arms in detail, identifying the young stellar associations and star-forming regions that mark these structures. The survey also revealed the distribution of dust in the disk, mapping the dark lanes that absorb starlight and re-emit it at infrared wavelengths. Beyond the disk, Hubble observations have probed Andromeda's halo, the diffuse outer region containing old stars and the debris of past satellite accretion. These observations have revealed a wealth of substructure, including streams, shells, and clouds of stars that trace the orbits of galaxies absorbed by Andromeda over cosmic time. The halo is not a smooth, uniform distribution, but a complex archaeological record of the galaxy's assembly history. One of the most striking discoveries in Andromeda's halo is the giant stellar stream, a vast ribbon of stars that wraps around the galaxy. This stream, first detected in 2001, is believed to be the debris of a dwarf galaxy that fell into Andromeda and was torn apart by tidal forces. The stream contains millions of stars spread across hundreds of thousands of light years, a ghostly remnant of a galaxy that no longer exists as a coherent system. Studies of the stream's stars have revealed their ages and chemical compositions, providing clues to the properties of the progenitor galaxy. Additional streams and substructures have been discovered through deep imaging surveys, each representing a separate accretion event in Andromeda's past. The galaxy appears to have consumed numerous smaller companions over its history, growing larger and more massive with each merger. This process of hierarchical assembly, in which large galaxies are built up through the accretion of smaller ones, is a fundamental prediction of modern cosmological models, and Andromeda provides one of the best laboratories for studying it in detail. The Hubble Space Telescope has also been used to measure the proper motion of Andromeda, the slow drift of the galaxy across the sky due to its motion through space. This measurement, announced in 2012, was a remarkable technical achievement, requiring the comparison of images taken years apart to detect shifts of only a few millionths of an arc-second. The proper motion, combined with the known radial velocity from spectroscopic observations, allowed astronomers to determine Andromeda's full three-dimensional motion for the first time. The proper motion measurement confirmed that Andromeda is heading almost directly toward the Milky Way, with only a small sideways component to its motion. This result strengthened the prediction that the two galaxies will collide rather than passing by each other, and it allowed more precise estimates of when the collision will occur. The measurement also provided information about the total mass of the local group, since the galaxies' motions are determined by their mutual gravitational attraction. Space-based observations at wavelengths other than visible light have added further dimensions to our understanding of Andromeda. The Spitzer Space Telescope, operating in the infrared, has mapped the distribution of dust and old stars throughout the galaxy. Infrared observations penetrate the dust that obscures visible light, revealing structures hidden from optical telescopes. Spitzer images show Andromeda's spiral arms traced by warm dust heated by young stars, as well as the smooth distribution of older, cooler stars that make up the bulk of the stellar population. X-ray observations from satellites like Chandra and XMM Newton have revealed the high-energy universe within Andromeda. These observations detect emission from hot gas, neutron stars, black holes in binary systems, and the supermassive black hole at the galaxy's centre. The X-ray view of Andromeda shows a population of point sources, many of which are X-ray binaries, where material from a normal star is falling onto a compact companion. The diffuse X-ray emission traces hot gas in the galaxy's halo and around regions of recent star formation. Radio observations have mapped the distribution of neutral hydrogen gas in Andromeda, the raw material from which new stars form. These observations reveal a complex structure, with the gas concentrated in the spiral arms and the star-forming ring, but also extending into a warped outer disk that may result from gravitational interactions with satellite galaxies. The total mass of hydrogen in Andromeda is estimated at several billion solar masses, enough to fuel star formation for billions of years to come. Ground-based surveys have complemented space-based observations by covering larger areas of sky and detecting fainter objects. The Pan-Andromeda Archaeological Survey, or PANDAS, used the Canada-France-Hawaii telescope to map the outer regions of Andromeda and its satellite system. This survey discovered numerous new satellite galaxies, stellar streams, and other substructures, greatly expanding our knowledge of Andromeda's extended halo and its family of companions. The PANDAS survey also contributed to the discovery of the plane of satellite galaxies around Andromeda, the thin, rotating structure that contains many of the galaxy's companions. This unexpected finding has generated considerable scientific interest and debate, as standard cosmological models do not predict such organized structures. The origin of the satellite plane remains uncertain, with proposed explanations ranging from the accretion of satellites along cosmic filaments to the debris of ancient galaxy collisions. Recent observations have also refined our understanding of Andromeda's mass and its comparison to the Milky Way. For many years, Andromeda was thought to be significantly more massive than our galaxy, perhaps twice as massive or more. However, more precise measurements using various techniques have suggested that the two galaxies are more similar in mass than previously believed. Some studies even suggest that the Milky Way may be slightly more massive when dark matter is included, though this remains uncertain. The question of relative mass has implications for the future collision between the galaxies. If the Milky Way is more massive than previously thought, it will play a more equal role in the merger, and the final product may retain more characteristics of our galaxy. The dynamics of the collision, including the timing and the trajectories of the galaxies, also depend on the mass distribution, making accurate mass measurements important for predicting the future. One of the continuing mysteries of Andromeda involves its history of star formation. The galaxy appears to have experienced a significant burst of star formation about 2 billion years ago, producing many of the stars now seen in its disk. The cause of this burst is not entirely clear, though one possibility is a close passage or collision with another galaxy, perhaps M32 or a now absorbed companion. Understanding this event could provide insights into the processes that trigger star formation in galaxies and the role of interactions in galaxy evolution. Another mystery concerns the origin of Andromeda's prominent ring of star formation at 32,000 light-years from the centre. This ring, visible in infrared observations, contains a high concentration of young stars and star-forming regions. Some astronomers have proposed that the ring was created by a head-on collision with M32, which passed through Andromeda's disk and triggered a wave of star formation that propagated outward. Others suggest alternative explanations involving internal dynamics or interactions with other satellites. The true origin of the ring remains debated. The supermassive black hole at Andromeda's centre also presents puzzles. Despite its large mass estimated at 100 to 230 million solar masses, the black hole is remarkably quiet, producing far less radiation than would be expected if it were actively accreting material. The reason for this quiescence is not fully understood. One possibility is that the gas supply near the centre has been depleted, leaving little material for the black hole to consume. Another is that the gas is present but is not efficiently funneled into the black hole due to the dynamics of the central region. The double nucleus of Andromeda, with its two distinct peaks of light, adds another layer of complexity. The currently accepted explanation involves an eccentric disk of stars orbiting the black hole, but some details of this model remain uncertain. Alternative explanations, including the possibility of a second, smaller black hole, have not been entirely ruled out. High-resolution observations with future telescopes may help clarify the structure and dynamics of this unusual region. Looking to the future, new observatories promise to revolutionize our understanding of Andromeda once again. The James Webb Space Telescope, launched in 2021, offers unprecedented sensitivity in the infrared, allowing observations of cool stars, dust, and distant background galaxies seen through Andromeda. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct a decade-long survey of the southern sky, detecting variable stars, transient events, and faint structures in Andromeda and other nearby galaxies. The next generation of extremely large ground-based telescopes, including the Extremely Large Telescope in Chile and the 30-meter telescope planned for Hawaii will provide angular resolution surpassing even the Hubble Space Telescope. These instruments will be able to resolve individual stars in Andromeda with extraordinary clarity, measuring their motions, compositions, and variability. They will probe the central regions of the galaxy in unprecedented detail, potentially resolving the mysteries of the double nucleus and the quiescent black hole. Space-based gravitational wave observatories, such as the planned Laser Interferometer Space Antenna, or LISA, will open an entirely new window on the universe. LISA will be sensitive to gravitational waves from merging supermassive black holes, including the eventual merger of the Milky Way and Andromeda's central black holes. While this event lies billions of years in the future, LISA will detect similar mergers in distant galaxies, providing insights into the processes that will one day transform our own cosmic neighborhood. The study of Andromeda is not merely an academic exercise, but a way of understanding our own galaxy and our place in the universe. Many properties of the Milky Way are difficult to measure from our position within it, but Andromeda offers an external perspective on a similar system. By studying Andromeda's structure, stellar population, satellite system, and dark matter halo, astronomers gain insights that can be applied to our own galaxy. Andromeda serves as a mirror, reflecting back knowledge about ourselves. As observations continue and new discoveries emerge, the Andromeda Galaxy will undoubtedly reveal further surprises. Every generation of astronomers has found something unexpected in this nearby spiral, from Al-Sufi's Little Cloud to Hubble's Cepheids to the modern discoveries of stellar streams and satellite planes. The galaxy that has accompanied humanity through all of recorded history still has secrets to share, mysteries that will occupy scientists for generations to come. Chapter 12. Observing Andromeda and reflecting on our cosmic connection. For all the sophisticated technology that modern astronomers bring to bear on the Andromeda Galaxy, there remains something profoundly moving about observing it with nothing more than the naked eye. On a clear moonless night, far from the light pollution of cities, you can step outside, look toward the constellation that bears the name of an ancient princess, and see a faint fuzzy patch of light that is actually an entire galaxy, 1 trillion stars gathered into a cosmic island over 2 million light-years away. This simple act of observation connects you to every human being who has ever looked up at the night sky and wondered about that mysterious glow. The Persian astronomer Al-Sufi saw it over 1,000 years ago and recorded it in his Book of Fixed Stars. Countless generations before him must have noticed it as well, even if they left no written record. When you observe Andromeda, you participate in a tradition of wonder and curiosity that stretches back to the dawn of human consciousness. Finding Andromeda in the night sky is not difficult once you know where to look. The galaxy is visible from the northern hemisphere during autumn and winter, when the constellation Andromeda rides high in the evening sky. The easiest way to locate it is to start from the Great Square of Pegasus, a prominent asterism formed by 4 bright stars arranged in a rough square. From the northeastern corner of the square, a chain of stars extends toward the northeast, marking the constellation Andromeda. The galaxy lies just off this chain, appearing as a faint, elongated smudge to the naked eye. Under truly dark skies, Andromeda is one of the most distant objects visible without optical aid. The light entering your eyes has travelled for over 2.5 million years, crossing the vast gulf of intergalactic space to reach you. When that light began its journey, the genus Homo had not yet appeared on Earth. The photons you perceive tonight are ancient messengers, carrying information about a galaxy as it existed in the deep past. Binoculars or a small telescope reveal more of Andromeda's structure. Through binoculars, the galaxy appears as an elongated glow, brighter in the centre and fading toward the edges. The two satellite galaxies, M32 and M110, may be visible as small faint patches nearby. A telescope shows additional detail, including hints of the dust lanes that cross the disk and the bright central bulge that houses the supermassive black hole. Larger amateur telescopes, under excellent conditions, can reveal even more. The spiral arms become visible as subtle variations in brightness, and individual star-forming regions may be glimpsed as tiny knots of light. The globular clusters that orbit in Andromeda's halo appear as faint fuzzy points, each one a dense collection of hundreds of thousands of ancient stars. Observing these details requires patience, dark skies, and well-adapted night vision, but the rewards are a deeper appreciation of the galaxy's structure and scale. Astrophotography has opened Andromeda to observers who might never see such detail visually. Modern digital cameras, mounted on tracking telescopes, can accumulate light over minutes or hours, revealing the galaxy in stunning detail. Amateur astrophotographers routinely produce images showing the spiral arms, dust lanes, star-forming regions, and satellite galaxies with clarity that rivals professional observatories of a few decades ago. These images, shared widely on the internet, have brought the beauty of Andromeda to millions of people who might never observe it directly. The experience of observing Andromeda, whether with the naked eye, binoculars, a telescope, or through photographs, invites reflection on our place in the universe. Here is an object containing 1 trillion stars, each one a sun potentially orbited by planets, located at a distance so vast that light itself requires millions of years to cross it. Yet we can see it, study it, and understand something of its nature. This is a remarkable achievement of human curiosity and ingenuity, a testament to our species' drive to comprehend the cosmos. The Andromeda Galaxy also reminds us of the vastness of time as well as space. The light we see tonight left the galaxy over 2.5 million years ago, but the galaxy itself is far older. Andromeda formed in the early universe, perhaps 10 billion years ago or more, and has been evolving ever since. It has witnessed the birth and death of countless generations of stars, the formation of planetary systems, and possibly the emergence of life on worlds we will never know. Its history dwarfs not just human civilization, but the entire existence of life on Earth. Looking forward, Andromeda will continue to evolve for billions of years to come. It will eventually collide with our Milky Way, merging into a new galaxy that will persist for trillions of years until the last stars burn out. The atoms that now make up Andromeda's stars, planets, and any life they might harbour will be recycled through future generations of stars, dispersed into space, and perhaps incorporated into new worlds. Nothing in the universe is permanent, but everything is connected through the endless cycling of matter and energy. This perspective can be humbling, but it can also be inspiring. We are part of this cosmic story, made of atoms forged in the hearts of stars, living on a planet orbiting one star among hundreds of billions in a galaxy that is itself one among trillions. The Andromeda Galaxy, shining softly in the autumn sky, is a reminder of the grandeur and beauty of the universe we inhabit. It invites us to look beyond our immediate concerns and contemplate the larger context of existence. The study of Andromeda has also taught us much about ourselves. By understanding this external galaxy, we have gained insights into our own Milky Way, which is difficult to study from our position within it. The structure of spiral arms, the distribution of dark matter, the processes of star formation and galaxy evolution, all of these have been illuminated by observations of Andromeda. Our neighbour serves as a laboratory, a comparison point, and a mirror reflecting our own cosmic home. the future holds the promise of even deeper understanding. New telescopes and observational techniques will reveal details of Andromeda that are currently invisible. Theoretical models will become more sophisticated, explaining the complex processes that shape galaxies over cosmic time. Perhaps one day, spacecraft will venture beyond the solar system and provide new perspectives on our galactic neighbourhood. The story of Andromeda is far from complete. It is a story still being written by astronomers around the world. As you contemplate the Andromeda Galaxy, whether through direct observation or through the words and images of others, allow yourself to feel the wonder that has drawn humans to the night sky throughout history. This is the same wonder that motivated Al-Sufi to record his observations 1,000 years ago, that drove Edwin Hubble to spend long nights at the telescope, and that continues to inspire astronomers today. It is a wonder rooted in curiosity, in the desire to understand, and in the recognition that the universe is far stranger and more beautiful than we could ever have imagined. The Andromeda Galaxy will continue to shine in our night sky for billions of years, a constant companion to whatever beings might gaze upward from Earth or its successor worlds. It will grow larger and brighter as it approaches, eventually filling the sky with its light before merging with our galaxy to create something new. Through all these changes, it will remain a source of wonder, a reminder of the vastness of the cosmos and the privilege of being able to comprehend even a small part of it. And so we come to the end of our journey through the story of the Andromeda Galaxy, from its first recorded observation by a Persian astronomer over a millennium ago to the cutting-edge research of modern astrophysics. We have explored its structure and stellar population, its satellite system and dark matter halo, its supermassive black hole, and its inevitable collision with our own Milky Way. We have seen how the study of Andromeda has transformed our understanding of the universe and our place within it.